です。
Ladies and gentlemen, distinguished guests, session will start in 5 minutes. Ladies and gentlemen, distinguished guests, session will start in 5 minutes. Ladies and gentlemen, distinguished guests, session will start in 5 minutes. Ladies and gentlemen, distinguished guests. Ladies and gentlemen, please find your seat. We are starting shortly.
Hello, everyone. Good morning, colleagues. My name is Musa Al-Kaltham from the IEA and Incident Emergency Center, and I have the pleasure of serving as the technical officer for this session. As we begin the fourth and the final day of the conference, I would like to briefly underline the importance of today's topic: termination, recovery, and long-term response mark the critical phase where emergency actions transition into sustainable recovery. So it's here that the science, governance, and community needs, let me say that again, it's here that science, governance, and community needs must align to restore safety, confidence, and normality. The discussions we will have today are essential to strengthen that pathway. It's now my honor to introduce our session chair, Dr. Gerd Durkin, head of the Soil and Water Management and Corp Nutrition Laboratory at the Joint FAO IEA Center. Dr. Gerd, he is for nearly 15 years, has led pioneering work in preparedness for managing the impacts of nuclear emergencies to food and agriculture. His work focusing on monitoring, remediation, decision support systems, and capacity building. Please, ladies and gentlemen, join me in welcoming Dr. Durkin to the stage together with our distinguished speakers. Dr. Gerd, please, distinguished speakers.
Good morning, colleagues. This is the last day, and I'm very pleased to see so many of you with so much energy still being with us, so that is really nice. Welcome to the session, the second session on termination, recovery, and long-term response. And Musa already indicates some points which are very important. So this session addresses one of the most critical phases of emergency management, the transition from response to recovery and long-term remediation. The termination is not simply the end of an emergency. It is the beginning of a complex process that involves restoring normality, rebuilding trust as well, and ensuring sustainable recovery for affected communities. Today we will explore practical strategies and scientific approaches for managing residual contamination, supporting agriculture and food safety, but also implementing remediation measures that are both effective and socially acceptable. Our speakers will share lessons learned from international frameworks, national experiences, and innovative research from soil remediation techniques to decision support systems and recovery planning. These insights will help us understand how science, governance, and community engagements converge to shape resilient recovery pathways after nuclear or radiological emergencies. And now it's my honor to invite as well the first speaker. The first speaker is Genaro Rodrigo Salinas Mariaca from the United Arab Emirates. He will speak about the termination of nuclear and radiological emergencies, a holistic perspective from emergency declaration to recovery and remediation. Rodrigo Salinas is with the Federal Authority of Nuclear Regulations, bringing expertise in regulatory frameworks and integrated approaches to emergency termination and recovery planning. He brings over 25 years of experience on emergency preparedness and response. 7 of them were at the IEC Centrum, and for the last 9 years, he is with the Federal Authority for Nuclear Regulations in the UAE. Welcome, Rodrigo, you have the floor.
Thank you very much, Mr. Chair. Good morning, everyone. Sabah al-khair. I know I have only 10 precious minutes, but I need to make a personal note about my name. Everyone was asking me, who is this Genaro Rodrigo? Genaro Mariaca, actually. My full name is Genaro Rodrigo Salinas Mariaca, but let's not go into those Bolivian complications. Yeah, Rodrigo, I usually go for Rodrigo Salinas. Okay, let me just mention that first, that what I'm going to present came out of our experience when developing a regulatory guide on termination. We are working, and our main basis is the IAEA document. But when working on this is on its final phase, we started to face some challenges in terms of terminology, concepts, definitions. And what I'm going to present is mainly about to present this holistic approach that we are trying to follow. I would like also to mention that I have the honor of presenting this, but Mohamed Al-Marzuki, head of the Emergency Response and Response Section, and Ali Al-Remeti, senior specialist, were also supporting on this effort. And here I would like to highlight that this doesn't intend to criticize whatsoever IAEA documents, because I fully agree with the statement that was made by the Vice President of the conference, saying that the history of the IAEA in terms of EPR is successful. And that success is somehow reflected into the GSR Part 7. So let me start with GSR Part 7. And one interesting thing that we were asking is, when is the recovery, the remediation going to start? And we're trying to find the link between the emergency phase and this recovery and remediation. And if you see the 100 most common terms in the IAEA, the recovery and remediation, of course, are not there. And we fully understand that because it's not the core of the GSR Part 7, right? GSR Part 7 is focused on emergency exposure situation, not on plan, not on existing. So that's understood. However, those terms are barely referred in the GSR Part 7. One is referred one, the other one is referred only 3 times, are not defined. But as I said, we fully understand the complete differences that we need to establish. Then we went to the next reference, which is the IAEA glossary, which is broader, right? It not only considers emergency, but it considers other exposure situations. And similarly, you can see here the 100 most common terms in that glossary, and still the terms I was making reference there are not there. Remediation, for instance, is well defined, has a definition. Recovery, however, is not. So for us, that was somehow a second flag in terms of how can we integrate this in a holistic approach? Because when you when you interact with first responders or with disaster management agencies, they are going to tell you, we will start with recovery actions as soon as possible. They will not wait for the emergency to be terminated. Now, in general terms, and let me summarize somehow how the the IAEA approach in terms of the different emergency situations I was making reference to. I think we all know that we refer mainly to planned, emergency, and existing exposure situations depending on the severity of the emergency. In terms of the phases, IAEA documents focus on the urgent, early, and transition phase fundamentally, and then whatever is before is the preparedness. And in terms of duration, we have there the specific durations, and I don't intend to go into those details, but let me also refer to somehow our approach in terms of trying to make some elements clear. First, the early phase, which we fully follow, and this is definition. This is not too much concepts. It's more about an intermediate phase that we want to make it clear for first responders in particular. And in terms of once the emergency is terminated, indeed we transition to existing or to planned. However, if we go to the preparedness phase, again, trying to implement the lessons learned, we need to have this coexistence with recovery and remediation, post-emergency recovery and post-emergency remediation. And also, we need to consider the different protective actions to reduce or avert doses. And here, and this doesn't intend to be a lecture about the protective actions, but the only thing I wanted to highlight here is that the different type of protective actions, like precautionary actions, by default actions, they are not only to be focused on the respective phase, on the urgent phase. The same with the urgent actions, right? They may start very early, but they may last until almost the end of the emergency, which is, if you see the approach in the different documents, that's going to be the case, right? Like relocation, that may last several months. And what we are trying to add here, and you can see that in the last two yellow arrows there, it's to highlight that recovery and remediation are going to start as early as possible. Now, I know this may be debate in terms of definition, but we also thought it's more about concepts. And let me support that in the next slides as well. That's only a reference about the shape, the meaning of the shapes. Now, let me make some remarks here. It's clear that emergency exposure situation has specific well-defined boundaries, from declaration to termination, right? Fukushima started in March 11, 2011. It finished in December 16, when all units were in cold shutdown. There's a specific period of time. Beyond immediate mitigation, a core goal of emergency, that's also in GSR Part 7, also includes prepare for resumption of normal social and economic activity. That we all agree. However, recovery and remediation do also coexist with emergency response, rather than being strictly sequential, one after the other. The current approach in the literature suggests that recovery and remediation, including cleanup, rehabilitation, and restoration, that I'm not referring to much, are measures to be taken after emergency is terminated. It suggests so, but it's not clearly defined. Now, what do we consider a holistic perspective here? Effective management of nuclear radiological emergencies indeed require a clear distinction between the different phases. Although an integrated approach to emergency management is being implemented by all of us, its significance remains underemphasized and may need greater visibility and strategic prioritization. Now, what would be the, I'm looking at the watch because the chair was very strict about the timing. What would be the way forward here? We consider we should be very cautious in terms of an early integration of recovery and remediation. Indeed, mitigatory actions, protective actions, other response actions that are going to be taken during the emergency should proactively incorporate consideration of recovery and remediation. And again, this came from our interactions, for instance, with first responders and disaster management organizations like in our countries in CIMA. And an interesting point they made was, they said, Rodrigo, we will start with recovery as soon as possible, right? But the concept we always have is let's wait for the emergency to terminate to go to this recovery phase. However, if you think about this, their point is valid, and this is the point where it's not only definition, but it's about concepts. Their point is, for instance, we need to restore basic services like electricity and water in a large emergency as soon as possible, and that's indeed a recovery action. And are they going to wait for a termination of the emergency? Absolutely not. Is this only concept or wrong definitions? Something that we need to consider. Now, and that goes to the second point that I'm making here as a final remark, to consider the mandate for early action. Those disaster management organizations and first responders have this mandate to start this remediation and recovery as soon and as early as possible, and not necessarily after the emergency is terminated. And the final point is about further guidance. And here I want, of course, to highlight that GSG 11, IAEA's GSG 11 guidance on termination, I would say it's one of the only concrete documents that focuses on termination. It focuses even beyond termination, which is something interesting, but it's also a challenge at the same time. But additional guidance is needed. And we were hearing about this additional guidance in previous presentations and in previous sessions. And we consider that, in particular, for this recovery and remediation, we need to make it clear, because we cannot have only terms that are going to be for the technical community, but it has to be well understood by the whole community that is going to be involved on emergency preparedness and response. So those would be our three main way forward messages that I would think that's exactly, I think I'm 1 minute more, but you can forgive me for that. Thank you very much.
Thank you, Rodrigo. Thank you very much. Our next speaker is Takuro Shinano from Japan. He will speak about exchangeable cesium 137 plays a key role in the transfer of radiocesium from soil to plants. Professor Takuro Shinano is from the Hokkaido University in Japan and is specialized in soil science and plant nutrition. His research focuses on radiocesium transfer and sustainable agriculture with extensive international collaboration following the Fukushima accident. Takuro-san, you have the floor.
Okay, thank you, Chairman. I'm going to talk about slide here. Yeah. Today I'm going to about from two aspects. One is from soil and one is from plant side. And both of them, the availability of radioactive cesium is the most important point to mention. And I'd like to talk about the importance of exchangeable radioactive cesium in the soil at first. This picture was taken about 1 year after the accident in Fukushima Prefecture. And during that time, during the 2011, agriculture scientists in Japan are involving into develop some strategy to encounter the radioactive nuclide contamination to the agricultural field. One of the most important points to initiate agriculture activity in the Fukushima area, that where the radioactive nuclide contaminated area, we need to decide which area is able to initiate agriculture activity in 2011. Because the accident occurred in the March, and normally we plant rice plant early in the May. So during that, especially in the April, we are working hard to decide the area to initiate the agriculture activity. For that purpose, we use the data obtained after the global fallout. These data were taken by the National Institute of Environmental Science in Japan. And from 1960s, we've been obtaining data of the soil radioactivity and also the brown rice radioactivity. And based on those data, we can calculate the transfer factor. Transfer factor is one of the very simple and very important factor to predict how the plant absorbs radioactive, especially radioactive cesium from that soil. It is just dividing the radioactivity of the plant by the radioactivity of soil. And as shown in the right figure, it is said that during the when the several countries keep they keep doing the nuclear bomb experiment in the atmosphere, the transfer factor seems to be higher than 0.1. Sometimes it reached about 0.3 or 0.4. But after that, in 1990s or 2000, the transfer factor decreased dramatically and lower than 0.01 or 0.001. And as the explosion, hydrogen explosion in the Fukushima Daiichi nuclear power plant finished by the end of March, we consider that no further fallout from the nuclear power plant occurred in the Fukushima area. So we decided that the maximum transfer factor in Japan will be 0.1. So based on that, and at that time, the provisional regulation value for the brown rice was 500 becquerel per kilogram. It is now 100 becquerel per kilogram, but at that time, 500 becquerel per kilogram. And based on the transfer factor and the regulation value, it is very easily calculated that if the soil is lower than 5,000 becquerel per kilogram, it is able to initiate agriculture activity. So 2011, we have initiated the rice planting in the contaminated area also. But unfortunately, there is some brown rice exceeded 500 becquerel per kilogram in the autumn of 2011. And those researchers in the Fukushima prefecture initiated the investigation why this occurred. And one of the reasons is that shown in the right figure, that those areas where the relatively higher radioactive containing brown rice found, the soil radioactivity was higher than 5,000 becquerel. That is one of the reasons. But for us, I mean that for the, especially for the plant and soil scientists, the most interesting and most important point is that the transfer factor seems to be higher than 0.1. Yeah, in this area. Sometimes it reached to 0.2 or 0.3. But as the nuclear power plant explosion has finished, we have some mistake for understanding the transfer factor from this result. And by analyzing the physicochemical soil analysis data, the researchers has reached to that exchangeable potassium level was the most important factor to regulate the accumulation of radioactive cesium from the soil. And based on that idea, government has decided to apply huge amount of potassium fertilizer to the soil. It is far more requirement for the plant, just to regulate the radioactive cesium concentration in the soil, because by the competition with the potassium ion, the accumulation of the radioactive cesium can be reduced. And this procedure has been carried out still now, but after we have been still continuing the investigation on the relationship between the exchange of potassium and the transfer factor, and we found that there is some very strange behavior between the soil types. In the red color, it is called Hamadori area. It's close to the Pacific Ocean, where the nuclear power plant existed. And when compared to the data of the blue area, this is middle of the Fukushima prefecture, there is a clear difference of the transfer factor and exchange of potassium relationship. Even at the same exchange of potassium level, the transfer factor seems to be higher in the area of the Hamadori, near the Pacific area. To explain this one, we introduced the idea of the exchangeable radioactive cesium concentration in the soil. The time is not so much. I would like to skip a lot of the mechanical data. But look at the right figure. If we apply the ratio of the exchangeable radioactive cesium to exchangeable potassium level in the soil at the horizontal axis, and the shoot radioactive cesium concentration is highly positively predicted. And this is the reason that we are focusing on the meaning of the exchangeable radioactive cesium in the soil. And it is quite realistic to introduce exchangeable fraction of the cesium, because as you know that in case of the predicting the potassium uptake by the plant, we normally use the exchangeable fraction of the soil to predict how the plant can absorb potassium from the soil. It's a quite similar idea for the radioactive cesium also. So we applied exchangeable radioactive cesium is one of the good indicator to predict the radioactive cesium uptake by the plant. However, there's a problem. To estimate the amount of the total radioactivity of soil is rather simple. We can utilize air dose rate to predict it. However, in the case of the exchangeable fraction of radioactive cesium in the soil, we need to extract fast, and we need to analyze the solution by using the germanium semiconductor or NAI detector. It takes time. It's not useful for under the emergent condition like in Fukushima. So we need to develop some other technique to predict the ratio. So we are initiating the research by using Mills technique. Mills technique is here. Yep. By the help of the Frank, we will have a talk later. And by using Mills, we are now trying to develop model to predict the ratio of the exchangeable radioactive cesium concentration to total radioactive cesium concentration. If we succeed this, we can estimate the potential of the soil to supply radioactive cesium to the plant. However, we have another problem from the plant side. Because this is data obtained from the 7 years monitoring data in Fukushima Prefecture. And this figure shows the exchangeable potassium level and the transfer factor of different plant species from left rice and soybean and buckwheat. It is clearly said that the soybean and buckwheat has a higher possibility to absorb radioactivity even in the same nutrient condition, the potassium condition in the same field. That is one of the difficult problems to decide which plant species is available to grow in the contaminated area. And to make clear, we are doing some experiment by using hydroponic culture and using stable cesium to have obtain the coefficient of each plant ability to absorb cesium from the solution. And this is one of the cases that I use komatsuna spinach and bok choy. Komatsuna is one of the plant of the brassica napas. And we clearly show that there is a quite different characteristic on each plant species. And by obtaining this coefficient, we can calculate the actual radioactive cesium concentration in the field condition. As shown here, we use the data of the exchangeable radioactive cesium concentration and the exchangeable potassium concentration in the soil, and that absorption factor or coefficient factor of the plant. And the figure shows the actual data obtained by different soil types and using komatsuna plant. And prediction value and observed value seems to be pretty significant. So we think that this method can be utilized for the determination of the which plant species is available to use.
So 1 minute
soil.
more?
Okay. Yeah. And 1 minute then? Okay. So I think that we will focus on the nuclear accident in the future, of course. And based on our experiments in Japan, I'd like to mention that at the emergent condition, we need to have a very quick decision for the where it is possible to grow the plant and which plant species is available to grow there. And finally, I'd like to mention about acknowledgement, especially for the help of the CRP project in FAIA. And also, here is Hisai Fujimoto, who has been initiated this experiment, but she has decided to come to the IAEA for 1 year, but because of COVID-19, she couldn't come here. And then Ayane, she went to IAEA, and now Kazu is staying in IAEA from just beginning of December. And Amelia is also helped us for the activity in the IAEA. And I forgot one important person here. Junpei is studied as an intern for 1 year in IAEA. Because he is not here, nobody will tell you about that. Thank you. Anyway, thank you very much.
Our next speaker is Fatima Damlakan from Saudi Arabia. She talks about investigating the potential use of different absorbents to mitigate soil contamination. Fatima is a research intern at the King Abdulaziz City of Science and Technology, and her work explores innovative absorbent materials for soil remediation of radiological contaminants. Fatima, you have the floor.
Good morning, everyone. Okay. Let me start by asking you a very important question. What do brain damage, kidney failure, and cancer all have in common? Unfortunately, in many parts of the world, the answer is the soil beneath our feet. This is because toxic substances are seeping into our earth and rising into everything we eat. However, hope is not lost. We are investigating special minerals called adsorbents. Adsorbents act like magnets in the soil. They attract pollutants, lock them into their structure, and stop them from spreading any further. Sorry, by the way, I had a different PowerPoint prepared, and they put a different one, but I'll just try to wing it. So basically, I'd also like to point out a very important note that there's a big difference between adsorption and absorption. Basically, in the process of adsorption, any adsorbed substance binds onto the surface of the adsorbent. It doesn't go through the membrane, like with absorption. And this process depends on many different factors like chemical affinity, ion exchange capacity. All of these factors help us determine whether it's a chemical adsorption or physical adsorption that is taking place. And this exact process helps us determine the ideal combination of adsorbents for certain contaminants. And if you look at this image, you can see that the issue of soil contamination is not exclusive to one site. You can basically find it around any continent around the world, which highlights the urgency of addressing this issue. Now you might tell me, Fatma, we already have different soil decontamination methods like thermal treatment or soil excavation, but these are all very costly and inefficient methods. Adsorption-based remediation is an on-site remediation technique, meaning that we can simply spray the adsorbents onto the soil and they simply do their magic. Our methodology includes spiking our soil several times by tweaking the levels of the adsorbents, the contaminants, the soil depth, and the masses, just very different variables that we kept on tweaking and editing several times, running it through the ICP-MS machine to test the levels of adsorption and contamination and many percentages. We also tested the soil under the scanning electron microscope to observe the structure of the soil before and after the adsorption process. Our main adsorbents used are silicate, bentonite, and zeolite. Our main and most important results include one of our adsorbents, silicate, having binded 100% of lead in a sample. This is a very important result because it not only shows that our theory is 100% correct, but it also means that we can further develop into ideal application methods to integrate it into real-world use. Another important result is the fact that one of our contaminants, cesium, has consistently shown low adsorption behavior. However, with zeolite, it has shown an exceptional rate of 86% adsorption efficiency. This means that there's high potential for us to investigate ideal soil conditions like pH and temperature to maximize the efficiency. Finally, we have also discovered that whenever we apply silicate to a soil contaminated with lead, it must be less than 20% of the soil's mass, because whenever we exceed this limit, the adsorption differs by a dramatic amount, and this result will help us get closer to the ideal application ratio. These are images shown from our SEM analysis. If you look at the two corners in the top, the two photos in the top left corner, you can see that in the photo on the left, it's the soil before adding any additives. It's just a pure sample. And the photo right next to it, on the right, is the soil after adding the silicate adsorbent and the lead contaminant. As you can see, there's obviously a difference in the two photos. The difference is that the soil granules on the right have become more refined and more abundant. This means that the soil's health and fertility has increased. So let's recap. These adsorbents are not only eco-friendly, not only do they mitigate the pollution, but they also increase the crop's yield. And if you look at the two photos on the right, which are also from our SEM analysis, in the top photo, you can see the soil before, and in the bottom photo, you can see the soil after. As you can notice, in the before soil, there's no prevalence of lead. However, in the after soil, lead has prevailed with a 0.92% by mass composition. What does this mean? This means that the process of adsorption has in fact taken place. Because when we add the silicate and the lead into the sample, the silicate binds the lead onto its surface so that when we remove the solution, the lead still prevails in the sample, which causes the machine to identify its presence. This project can be applied in many instances, which include radiological precaution. Say, for example, you want to build a nuclear facility. Before doing so, you can spray the soil with the adsorbent so that if an accident were to occur, risk is minimized by a strong factor. Another instance is, I'm sure everyone in this room knows about the Chernobyl incident, where a nuclear reactor in Ukraine exploded and its effect kept on spreading to more areas and more countries. In an instance like this, we can use the adsorbents to create a barrier between the area of high radiological impact and areas it's bound to reach, so we can slowly decrease the rate of expansion of the contamination. Another instance is in agriculture. Many farmers like to use something called pesticides. Pesticides are good because they keep insects away from plants. However, those pesticides are very bad for human health. We can use the adsorbents to have the best of both worlds. Not only can you continue using the pesticides, but you can use the adsorbents to bind the pesticides onto their surface, stopping the plants from absorbing them. Finally, many countries like to excessively mine. And meanwhile, excessive mining does produce a large amount of precious minerals. It can also lead to the overaccumulation of unwanted and harmful substances that are already prevalent in the soil, so that when they concentrate in one area, they pollute the groundwater. So we can create adsorption-based water filtration systems to integrate into wells to create clean and drinkable water for the community. In conclusion, this is not just a theory, but an actual solution. We can reclaim poisoned lands, protect future harvests, and create new industries out of waste, all with just a handful of earth-friendly materials. Thank you for listening.
Thank you, Fatima, for this presentation. Now we will go to the fourth presentation given by Frank Albinet from France. And he will speak about This is for NAFA, a decade of decision support for nuclear emergencies affecting food and agriculture. Frank combines expertise in data science and emergency management with over 20 years of experience at the IEA and international organizations. He leads the development of decision support systems for food safety during nuclear emergencies. Frank, you have the floor.
Good morning, all. Just waiting a second for my presentation. Yes, good morning. I want to share a story, not just about a piece of technology, but what happens when you bring together people
Yeah.
who have faced major nuclear emergencies, and you bring them together to solve a big issue, which is the whole purpose of DSS for NAFA, which is how to improve decision making with regard to foodstuff restrictions and farmland remediations. Yeah, sorry. So DSS for NAFA has been built with people who were in the fields, who were in the labs, who were in the emergency rooms, making decisions under pressure. And what we learned from this is that the biggest issue is not really data, but the biggest issue is to bring data to the right people at the right moment. Let me explain what I mean by that. As all of you know, when a nuclear emergency affects food and agriculture, it involves many actors, from the fields, from data collectors, from the labs, from different ministries, ministries of health, ministries of agriculture, ministries of environment. And all these actors need to be coordinated. If we fail coordinating these actors, the result is pretty obvious. There is a lack of, there is an information overload, and most critically, there is a delay in decision making. So, to address this, we brought together. We developed, actually DSS for NAFA is, the main purpose of DSS for NAFA is to streamline data flow and to orchestrate these actors. So it means that with DSS for NAFA, it's a single entry point where data collectors go on the field and see what they need to collect. Labs get data and knows how to report the data. And along these data flows, the decision makers, they can, the decision makers, they can sense and probe this data flow, and we plugged data visualization tools like hotspot map, how to identify the hotspot, and how to project different scenarios. But it took time to create that. So we actually took more than a decade to create this tool. So we brought together along 2 CRPs, coordinated research projects, and with many member states. And most critically, we brought together people from Chernobyl and Fukushima who could identify the pain points, right? And so we spent a lot of time identifying the pain points and to finding the minimal core requirements to address those. For instance, I could give a trivial example, which is we spent 6 months identifying the core data model. For instance, again, it might seem trivial, but during the first stage of Fukushima, they were receiving a lot of false positive, and they were essentially receiving false positive because they were collecting samples close to the roads, right? So when we decided about what are the core attributes, we decided in particular to identify, for example, distance from the road. This seems trivial, but it's very pragmatic. Most recently, we have been involved in the Convex-3 exercise. So it allowed us to validate that actually DSS for NAFA could be deployed in a matter of 24 hours. Because we decided about, and by design we focused on simplicity, and we wanted to focus on the bare minimum. So in a matter of 24 hours, just getting the administrative units, the crop calendars and so on, the DSS for NAFA was ready to use. Unfortunately, it was a bit frustrating for us because DSS for NAFA really shines after these first 36 hours where it is important to decide about food restrictions. So yeah, it was a successful exercise for us, but a bit frustrating because we could not really exercise the DSF-1FA at this full power. However, we had confirmation of something we knew from day one, which is in such situation, we have to expect the unexpected. And for instance, the event took place, the exercise took place in June. So exactly at the time where the winter crops were about to be harvested, right? So it was highly important to have in a timely manner crop maps. Obviously, after 24 hours, the ministries and the FAO were not capable to provide such a map, but we had to wear our data scientist hat and to create such a map, and it was possible to do so in 1 hour. So here what I want to highlight is actually, however great is your tool, you need to be flexible and to have the right data science capabilities to cope with the variability of the situation, the unexpected, and the non-standard. So how do we scale this from a tool that a few of us have designed to something that the member state can use? And the response is to develop a sense of ownership and to jointly develop a common good. The DSF-1FA is actually a technical artifact which is available to all. We have not attached any open source license to it, but de facto it is open source. So you can use it, you can adapt it to your need, as we did, for example, in Belgium. You can add new features like we did with China, where we ingested a huge amount of satellite imagery to create crop maps at large scale, or you can install it on premises, right? And you can adapt and you can further improve it. This said, here I want to trigger a warning, which is a bit weird from a guy who has spent his own career to promote innovative technologies. But DSF-1FA is much more than a technical artifact. It's a philosophy, it's a vision. And DSF-1FA is just our best attempt, to exemplify it and to make it concrete. And hopefully I would have liked to present and to make a demo of all the capabilities and the visualization and the whole the workflow and the streamlined workflow. Nevertheless, we have a booth here, and we will be more happy than to show it in action. And so here we have actually a book, we have videos, and we can demo it live, and you can see with us if it's relevant to your use case, if we can improve it together, and let's go forward. Thank you.
Thank you, Frank. And this brings us to the fifth speaker. Lucas David Martire is our next speaker from the OECD, from the Nuclear Energy Agency. And he will speak about INEX 6, International Reflections on Long-Term Recovery Preparedness Following Radiological Emergencies. Lucas is a radiological protection specialist at the OECD NEA and scientific secretary for the Working Party on Nuclear Emergency Matters. He brings insights from global recovery exercises and policy development for long-term preparedness. Lucas, you have the floor.
Thank you, Chair, and thank you for the organizers for giving this space for share what was the 6th edition of the International Nuclear Emergency Exercise. So I am presenting this here, but this exercise was also the work of a big group of experts, mainly from Canada, UK, US, France, Portugal, and more. And it was organized by the Nuclear Energy Agency. So what is the Nuclear Energy Agency? It's an international organization composed by 34 member countries, together with some strategic partners. And it's composed by several technical standard committees I work for the Committee of Radiological Protection and Public Health, and beneath this committee is the Working Party of Nuclear Emergency Matters, which has been in charge of developing this exercise. For more than 30 years now, the first exercise was in 1993. Earlier, INEX exercise focused more in the early phase following an event, things like communication, protective actions, a bit of stakeholder involvement. But the sixth edition is the first one to be devoted solely to the long-term recovery. And why recovery? Particularly after the Fukushima accident, it was evident the complexity and the challenge that were faced by Japan. In CRPPH, in 2019, they established the expert group on recovery management. This group developed a framework. This is a very good document that you can access online. But one of the gaps identified in the report was that there is a general lack of long-term recovery exercise. There are several reasons for this, and one is that recovery exercises are very complex and very resource-intensive. But nevertheless, WPNEM embarked to planning and recovery exercise as INEX 6. They first established a group for the scope and the format, and finally in 2022, it was established the expert group on INEX 6 that was in charge of developing all the technical materials, designing the scenario, and all the material to share with the countries that they were doing the exercise. So how was the exercise? As mentioned before, it was focusing on long-term recovery. They put the players 1 year after the event. It was designed as a question-driven tabletop exercise, and the participants were asked to apply existing policies and plans in their countries. To tackle this complexity, there was 4 modules, like health, impact, food safety, remediation and decontamination, and waste management, together with some cross-cutting issues, like stakeholder engagement, communications, and international cooperation. And countries were able to choose if they want to play all modules or only a few. For sure, countries need to establish a national planning committees, and the participation on each module had to be tailored, as there are different organizations for different aspects. And after the countries performed the exercise, all the information was gathered with a questionnaire, a common questionnaire for comparison. So very briefly, what was the scenario? Was a transport accident. This was chosen to be relevant for both nuclear and non-nuclear states. Was a fire. There was a spread of contamination that led to public exposure. There was evacuation, business closed, and a very complex initial situation that the countries needed to face. So a snapshot of the participation. As mentioned, it was 26 participating countries and territories with 18 nuclear and 8 non-nuclear countries. And this is the module distribution. The food safety module was the most popular, and the radioactive waste management the less popular. This is also, when we were following up with the different evaluation events, in one way the countries want to test food safety because of their importance, but also it's a topic that all countries has a system and things prepared. In some of the other modules, some countries admitted we really don't have a framework for it, so wouldn't be able to play. So I apologize in advance that I'm going to go extremely fast, as we don't have time for go to the result, but it will be a report coming soon with more detailed evaluation. So as general result, it was confirmed that the majority of the country legislation does not require exercise in recovery. And also regarding to having or not having a recovery framework, this is inconsistency. Some countries have materials document, but not as a recovery framework, more like a part of the response plans with some procedures. The countries have a cooperation agreement, and they mentioned that they would seek international assistance, but there was a lot of confusion. For example, many countries mentioned that they would go to RANET for this. As we was mentioned before, like RANET is a tool, an excellent tool to operationalize the assistance convention, that this is a very specific thing for the emergency phase or the early phase. So it's not exactly to use during recovery, but even though the countries mentioned that they would like to have some kind of international assistance on this. Regarding stakeholder engagement, this is a very popular topic. All the countries mentioned that it's recognized as important, but when you go to try to look for a structured process in place, usually there is a lack of it. Same with recovery training. But the important point is all the countries found the exercise useful. For many of them, it was the first time they were testing recovery. And this is saying something that about the importance of it. Regarding the health impact, most countries have occupational dosimetry programs, but the non-occupational is not that exposure are not common. There are for sure concerns regarding the resources, the strain of the capacity, especially when you go to long-term monitoring and more. Regarding mental health and psychosocial support, most countries have something, but they were referring to more general mental health and psychosocial support strategies. As, for example, it was mentioned by Abel on the first day of the conference, nuclear accidents are quite particular. They carry stigma, they carry radiophobia, so they require the more tailored plans for psychosocial support, and this is something that is sometimes lacking. Regarding food safety, as mentioned, this was the most popular module. All countries have legal systems, but there are problems with the criteria for some of the countries. For example, we have codex, we have the European directives, we have domestic standards, and sometimes they are not the same. And this is a big problem, because if something happens, it will lead to public mistrust. And the European standards are sometimes more restrictive than codex. And the country has said why. It's very difficult to explain to the people. Regarding food monitoring and more on, the countries have resources, but yeah, with the conditions we explained in the scenario, some countries mentioned that they could be like overwhelmed with this and a potential strain of resources. And same with the lack of long-term food safety plans. Remediation and contamination, similarly, there are frameworks, sometimes roles and responsibilities that are not clear. Some countries, they don't have like prepared prioritization strategies or a formal remediation strategies, because they think, okay, it's a context-specific strategy that we could done in the moment. Nevertheless, there are countries that have more plans in place, and we think this is very useful. And yeah, more about resources. Waste management, there are frameworks that can be adapted, but there are very limited availability of transportation for waste. Temporary storage is something that usually is not predefined or pre-identified, and the criteria for acceptance of this low storage, sometimes there were some problems with it. So to sum up, cross-cutting finding, we mentioned resource planning, like the pre-established plan for securing and scaling resources. International coordination, we have the thing that countries would like to have it, but there is not clarity, as there is not an international coordination mechanism for recovery as well developed as RANET. For sure, if a country is in a recovery situation and asks for help, I truly believe that countries will help, and IIA has different mechanisms to help countries, but not exactly as RANET, as is out of the scope of it. Regulatory framework, we mentioned about these variations between international and domestic standards that could challenge the communication and the food trade, so it's a big problem. And some reference levels that they are inconsistent. And stakeholder involvement, as mentioned, very important things, but still need to be developed more. This is my final slide. We had last month in Paris, hosted by the French regulator, ASNR, a workshop. This was a very good workshop where we were able to present results more in 2 days, not in 10 minutes, and we were able to discuss about actions and next steps. all this will be summarized in the report that is going to be finished soon, and we hope to be published soon after this. It will be available, so please follow it will be published at NEA or in the countries that there are members. Your CRPPH delegate will have it and will be able to share it. And if not, you can send me an email and if I can send it to you. The report will summarize the exercise and summarize some of the action and recommendations. There is also the program of work of CRPPH and WPNEM that we are going to follow up on this. And finally, this is more a personal opinion, but I think all the people that was able to, as a player or as organizing this exercise, found it very useful. And we think that countries should have this, maybe not at the scale of this INEX exercise, but they do practice in regular basis recovery exercise. So thank you, and I will be open for questions later.
Thank you, Lucas. And this brings us to the last speaker, Tariq Fahad Al-Shahrani from Saudi Arabia. Saudi National Environmental Radiological Monitoring Program, he will speak about a comprehensive radiation baseline study and its role in future comparisons in emergency situations. Tariq is a nuclear engineer at the Nuclear and Radiological Regulatory Commission of Saudi Arabia with 6 years of experience. He earned his bachelor's degree in nuclear engineering and science from Oregon State University and works on national radiological monitoring and emergency preparedness. Tariq, you have the floor.
Thank you. Assalamu alaikum wa rahmatullahi wa barakatuh. Good morning, everyone. It is an honor to be part of this event. I would like both IAEA and NRC for giving me this chance. And our chairperson mentioned, I will share you with NRC journey in establishing the National Environmental Radiological Monitoring Program. So let's start with the overview of the program and its key objectives. Basically, the program is called EPR, which stands for the National Environmental Radiological Monitoring Program, and NRC aims to achieve 4 key objectives of this program. First, NRC aims to establish the National Environmental Radiological Baselines, which means NRC also will have the reference value in case of emergency situations. NRC also will providing the program outputs and finding with public. Transparency is one of NRC principles, and from this principle, NRC will share all the findings with public as open data. Finally, creating atlas map and contour maps are the targeted from this program. The Kingdom of Saudi Arabia is considered the 13th largest country in the world with an area of 2.1 million square kilometers, and the entire area is targeted in this program. So the entire kingdom is divided into almost 1,000 grid, or to be more specific, it is 986 grid. And each grid, as you can see in the slide, is 2,500 square kilometer because it is 50 kilometer by 50 kilometer. The entire Kingdom of Saudi Arabia is divided into 13 administrative regions, which is called in Arabic al-Manatiq al-Idariya. They are Riyadh, Eastern Region, Qasim, Hail, Northern Borders, Al-Jawf, Tabuk, Medina, Mecca, Asir, Al-Baha, Jazan, and finally Najran. And based on RRC assessment, we started with Riyadh regions in light yellow, and the mission completed in 2024. And for this year, we are done with Eastern region. And by the way, these 2 regions represent roughly 50% of the entire kingdom in terms of area. NRC aims to complete the remaining 11 administrative regions by end of 2028, hopefully. So what happens in each grid out of these 986? Let's find out. The team usually will leave NRC building early in the morning to the targeted sites. When they arrive, they will collect 2 types of samples. First, they will collect air sample. This is done by medium flow rate R samplers. They also will collect 2 soil samples at different depths. But also they will perform 2 types of measurements. They will do the radium measurement and the ambient gamma. The radium measurement is done by RAD7, while the ambient gamma is done by survey meters. All of us love the language of numbers, so here are some numbers. We collected more than 800 samples so far. Also, we performed more than 4,000 measurements so far. So, this is my favorite part of the presentation in RC laboratories, where I spend 40 hours a week. So let's start with the main objectives of these laboratories. Basically, NRC aims to establish the National Environmental Radiological Monitoring Program, the one that we are discussing right now. And laboratories will play an important role during this establishment of this program, especially when it comes to conduct radioanalytical analysis and measurement. Also, these laboratories will support NRC decision-making in emergency situations, as well as supporting NRC and other regulatory control processes, including, but not limited to, nuclear security and safeguard. So, I would start with our Gamma Lab due to its importance, especially in this program. Our Gamma Lab is equipped with more than 20 high-purity germanium detectors and sodium iodide, both fixed, portable, and handheld. Our second largest laboratory is the radiochemistry lab. It's equipped with 2 many systems, alpha spectroscopy, as well as liquid scintillation counters. Also, we have a dosimetry lab equipped with the 2 technologies, TLD and OSL. For elemental analysis, we have ICP-MS lab, as well as our XRF lab with the 2 technologies based on wavelength and energy. Also, we have a radon laboratory equipped with both passive and active systems and techniques. Also, air monitoring is one of the activities that we are carried on in our laboratories. For 2025, more than 12,000 samples have been analyzed in our laboratories. The big majority of these samples were analyzed in our Gamma Lab, almost 8,000 samples. Basically, without quality, these laboratories are just room with equipment, nothing more. And from this standpoint, NRC Laboratories has achieved ISO 17025 accreditation this year. And for people who are not familiar with this type of ISO, its international standards show that the laboratory can deliver and generate accurate, reliable, and internationally accepted results. The accreditation includes 8 measurements covering different laboratories, techniques, and sample types. Starting from 2 of them are for Gamma Lab, 1 for TLD cards, 4 for the radiochemistry lab, covering both liquid scintillation counters and alpha spectroscopy system. Also, 1 goes for our ICP-MS lab, and the last one is for sampling collection. Basically, our program that we are just discussing is based on ISO accreditations from the collection of samples and for generating reports and archiving. So the program outcomes, I'm only allowed to speak for 10 minutes and times go fast, so I will share with you this in brief. So starting from the radiation dose rate, followed by radon concentrations, the most important outcomes are the soil samples for both top soils and bottom soils. Starting from K30, potassium 40, cesium 137, thallium 218, and lead 2010. Also the isotopes for radium, thorium, and uranium. And these are the maps that we are generating. The blue one is for the radiation dose, while the radon is the green one. And we are showing just only one example for 235. Here are all the contour maps that we are creating for Riyadh region, not the entire kingdom, because as I mentioned earlier, we are done only with the two regions, Riyadh and Eastern region. So future work, as I mentioned, we are done with the largest two regions of Saudi Arabia, Riyadh and Eastern region. And NRC aims to complete the entire project by 2028 or 2029 as maximum, hopefully, and they will cover the remaining 11 administrative regions. But NRC also want to expand the scope to include water and food samples, which also be done by 2029. I would like to thank NRC CEOs and Dr. Nasser Al-Khamshi, the Vice President, for facilitating everything for us. And I would like also to thank our experts, Dr. Fahd Al-Masoud, Dr. Mansour Al-Murashid, Dr. Ibrahim Al-Hamarna, as well as Dr. Umar Al-Sagar. And because I work with a great team, thank you, Yusuf, thank you, Yahya, thank you, Ghazi, Salman, Abdul Aziz, Saud, Sharifa, Shahad, and all of the other team, because I'm lucky to be part of this team. I really appreciate your listening. Thank you.
Thank you, Tariq. And thank you to all our speakers. And this brings us now to, we have some time for questions and would like to open the floor for questions from the audience. I see there a question, so please kindly provide the microphone. Kindly invite to have a short question and a short answer from our panel members.
Good morning. This is Walid Al-Breki from Baraka Nuclear Power Plant from UAE. So I have a question regarding transition from emergency to recovery, and I saw the importance of have a clear process to transit from emergency to recovery. My question, what's the big risk of delaying that transition from emergency to recovery?
I will pass this question to Rodrigo.
Not to Rodrigo and IEA. I want to see IEA perspective also.
All right. But let's first ask our panels maybe to answer.
Okay. Thank you, Walid, for that question. Indeed, transition is a phase that it's been more and more clarified, I think, in terms of when does it going to start. Now, you are talking about when is this, what are the risks of delaying the start of the transition? I would say the earlier we start with the transition, the better, because that's the moment where we start considering elements that the ones I presented in my presentation, right? We start thinking about the recovery, we start thinking about the remediation. As soon as we have the situation stable, as soon as we know the radiological conditions of the emergency, it's the moment to start transitioning to an eventual either existing or planned exposure situation. So I would say there are essentially no major risks in terms of starting this as soon as possible. Hope that answers your question, your answer.
Thank you, Rodrigo. And I think I would also like to ask Takuro, because Takuro has been involved very much in remediation. You know, in Japan itself. What is your opinion about this aspect of the transition?
I think that it's completely depending on the condition of the radiation in the field. I mean that I'm being boring in the agriculture sector, but if we need to consider about the human health, it's completely different from that of that emergent condition. Because when considering about the agriculture sector, it is a bit later transition stage, I think. It's very important to consider to the food contamination, but it's different from the exposure from the outside. I mean that external radiation condition is completely different from. Based on that, we need to consider for the two phases for the to make the countermeasure for that. That's my idea.
Yeah, thank you very much. It's a complicated question, of course. It depends really on so much on the situation itself, but also the time from when the accident happens. When it happens, of course, in late summer, when all the agriculture is finished and is harvested, obviously, you know, you have more time as well for recovery, maybe for several months. But when it happens exactly at planting time, you know, the accident happens. It's a completely different story. Prohibition of planting may happen. as an intermediate phase. So it's really case by case, I believe, that we have to look at it. There is no one solution for every recovery phase, specifically in the context of food and agriculture. Thank you for this question, and I look at the room if there are more questions. Yeah, I see one question from Tristan. Tristan, I think it is.
Yeah, hey, good. Thank you.
Hi.
I have a question for Lucas. You presented that there's the exercise is available to any country if they wanted to exercise recovery tomorrow. Can you explain how they would do it to get the materials? I think there's player guides, there's evaluator guides, there's a scenario, and there's a list of questions. So I think the full package is there, but maybe help people figure out how to do that.
Yeah, thank you, Tristan. And yes, I mentioned that the NEA is composed of 34 countries, but all those documents are publicly available for all, and this is going to be the idea. First, the report of the exercise will be published, and also all the materials from the exercise, there is like package, like the scenario, the player guide, how to establish a national planning committee. This all is going to be referenced there in this report, but also in the NEA page you can look for it. But I would say that the report will be the main connection with all the different documents and reference on the exercise.
Thank you, Lucas. I'm looking in the room. There is another question. Yes, please.
Good morning, everybody. I would like to say that I'm very interested for these topics. I am from Iraqi regulatory body. We did the same project in Iraq for every year, but this is in the last. Bring the sample, return to our laboratory. There's a new mentality, we call that mobile detection system. It's very useful. We can get analysis and result directly. Thorium concentration, radium concentration, uranium, everything is very important and it's very useful. We can minimize the time and it's more quality. And after that, we make a comparison between mobile detection system and the same result. It's very interesting. I'm very interested for that. And if you want, we can compare this result from the Iraq. It will be very important. And thank you very much. And I know that you spent a lot of efforts to complete this presentation. Thank you very much.
Thank you. And I think I will, it is a comment, of course, but this leads me a little bit to a question for Tariq. And, a question, how does this program, because it's amazing what you have been doing there, or you are doing for the next years as well, and I'm very much interested as well in the outcome, but how does this program enhance national resilience and inform decision-making during radiological emergencies in case of a radiological emergency?
Yeah, so the environmental radiological monitoring program, it has a lot of parameters. The one that we are doing is the first step, which is the baseline, radiological baseline. With this baseline, you will never how much it goes when emergency situations happen. So it is important to know your normal level or radiological background normal level, just because you will know how much it goes up. Based on this, you will make your own decision in emergency situations.
Thank you very much. Yes, we have a few minutes more. Maybe I am trying to look with my bad eyes in the room to see if I still see a hand raised. I don't see. So let me ask a question to Frank. So DSS for NAFA, the system you have been developing, integrates different levels of decision-making in responding to nuclear emergency affecting food and agriculture. And what lessons have emerged from your R&D about integrating such technology with stakeholders' decision-maker engagement in food safety crisis? Something maybe interesting as well for NEA, looking that food safety was really at a high level, and I think there NEA and IEA have to sit together, I think. Yeah. So Frank, what do you think?
Yeah, thank you, Gerard. we were very lucky in this project because it was a long-term project, more than 10, almost 15 years. And we had a lot of partners and contributors. And from the beginning, we had the opportunity to address very focused use cases. A bit like we did with REMIS, where actually we had identified very clear needs, and we developed very focused solution and ad hoc and right to the point. And from the beginning, we highlighted the importance of having something very simple, robust, and replicable. I'm mentioning that because one of the biggest challenges from an IT point of view of this project is a life cycle difference between the period of the different accidents which happened these last decades and the life cycle of software, which is essentially a matter of 5 years, right? So keeping things very simple and modular and focus and developed in an ad hoc way with the ability to redevelop it from scratch, in a matter of months maybe. If today we had to redevelop DSS for NAFA, if you give it to me, a good team, we can redevelop it in 1 month, right? With the newest technologies. And so the lessons are this one, yeah, let's be focused, very modular, focusing on simplicity, and the system is just an artifact, and the artifact just flies, right? So, and we have to recycle and to do it again and again and again, and focusing on the vision, the philosophy, and the artifact is just a trivial stuff, I would say.
Okay, thank you. And last question, last but not least, Fatima, thanks for your presentation and your courage as a young scientist to do this, and it's really very good. So my question is, okay, you spoke about these amendments. What would be the economic scalability considerations for field application? Because at the end, in remediation, it's also about costs. What do you think about that?
Okay, so I basically was supposed to have this included in the original PowerPoint, by the way, but I'll address it. So these adsorbents are fairly cheap, considering their per unit cost. It obviously depends on each adsorbent. Like, for example, bentonite has the lowest per unit cost, making it ideal for farmers or agricultural use. And silicate is in the middle range of the per unit costs, making it perfect for urban or governmental projects, where usually in cities we have high levels of heavy metal contamination, and silicate is perfect for lead removal, which is a heavy metal. And finally, zeolite, having the highest per unit cost, despite that, it is exceptional in cesium removal, making it perfect for industrial zones where when accidents occur, cleanup is necessary. And as we can all infer, that any land that is contaminated immediately loses its value. However, when we remediate these lands, we therefore increase the land's value, so you can easily break even in a project where you use these adsorbents.
Thank you very much. This brings to the end, and Fatima, I would like to invite you to discuss as well with some of our colleagues in the room who works a lot on this aspect as well, so I'm sure there might be an interesting exchange of knowledge. So I would like to thank this panel for all your presentations and all your amazing answers, and would like to thank you for being here on Friday morning. It was my pleasure to share this, and I would like to ask an applause for our panel members.
بسم الله الرحمن الرحيم. في صدر قاعد أهمس.
واحد اثنين واحد اثنين واحد اثنين واحد اثنين. على هالخشب ابشر.
ومعبيها بطارية مضبوط.
Ladies and gentlemen, distinguished guests, session will start in 5 minutes. Ladies and gentlemen, distinguished guests, session will start in 5 minutes. Ladies and gentlemen,
Ladies and gentlemen, thank you for your patience and welcome to this session on communication with the public in nuclear or radiological emergencies. As you will be aware, over the last 4 days, this is a topic that has come up again and again as one of the central challenges of nuclear emergency response. And so I'm very, very pleased to be able to introduce to you this distinguished panel of experts to discuss this topic today. I'd like to now welcome our session chair. We're very privileged to have such an expert with us today. Mr. Gino Moonsamy is the Communication and Stakeholder Relations Manager at the National Nuclear Regulator of South Africa and serves as the Public Information Officer during nuclear radiological emergencies at his organization. He is also a long-standing partner of the IAEA on Public Communication in Emergencies. He is a member of the Global Nuclear Safety and Security Steering Committee and is also a long-standing chair of the GNSSCOM, the Global Nuclear Safety and Security Communications Network. And I should also mention that he is a program committee member of this conference and so has been involved in steering this conference since the very beginning. I'm so pleased to welcome Gino and to invite him to take over the coordination of this session.
Thank you for the introduction, Nayana, and thank you for this opportunity. Distinguished delegates, colleagues and friends, good morning and welcome to our session on communications during emergency situations. It is an honor to chair the second session dedicated to communications during emergencies, an area that sits at the very heart of public protection, institutional credibility, and effective emergency response. On the second day of the conference, we had a first session on communication during emergencies. During that session, we heard presenters share various perspectives on communication during emergencies. Today, we expand the sharing wider as we continue building the future in an evolving world. In nuclear and radiological emergencies, the technical response is only half the challenge. The other half, often the most decisive, is how we communicate, how we inform people, how we build trust, how we counter fear, and how we guide communities when uncertainty is at its highest. In an age of social media surge, misinformation storms, and instant global scrutiny, communication has become a strategic capability, one that can either strengthen public confidence or erode it within seconds. That is why this session is so vital. Our mission today is not to simply to share good practices. It is to future-proof our communication strategies for a world that is changing faster than ever before. To help us to do that today, we are privileged to have a truly global panel of speakers, each bringing real-world insights from different national contexts. From Cuba, we will hear how they apply audience research. From the United States, we gain various perspectives on creating a new culture for risk communication. From Nigeria, we will learn on policy frameworks for public communications. From Indonesia, we'll explore multi-stakeholder communications. From Turkey, we listen to institutional approaches to risk communication and cross-sector collaboration. And from the IAEA, we'll get the global synopsis with a deep dive into AI tools managing misinformation and disinformation. Together, these voices form a powerful tapestry of knowledge, north, south, east, and west, reminding us that while our regions differ, our challenges in nuclear emergency communications are shared. So I invite you as the audience to lean in, to participate actively, and to think boldly. Let us use this moment to strengthen our collective readiness, sharpen our communication tools, and build the trust that is essential for nuclear and radiological emergency management worldwide. Thank you, and now let's begin. So, the order of speakers today is Indonesia, Turkey, Cuba, Nigeria, USA, and the IAEA. So I'm going to first introduce the first speaker. I'd like to invite Randy Batubara. Randy is the national manager. Randy is the manager of National Vital Object Security within Indonesia's National Research and Innovation Agency. He is responsible for emergency management and the coordination in science and technology facilities. He will discuss Indonesia's experience in strengthening multi-level communication systems for radiological emergencies. Randy? You can sit. Oh, you can go there, it's fine.
Assalamualaikum warahmatullahi wabarakatuh. Sabahul khair. Good afternoon, ladies and gentlemen, the participant, the audience of International Conference on Nuclear and Radiological Emergency. Thank you, Mr. Chino, as chairman of this session, and also Ms. Nayana as technical support from IAEA for this session. And thank you for Riyadh. I'm so glad to be here. And for the organizing committee, Shukran Katsiron. I'm Randy Tondi Pandapotan Batubara. I know it's a long name, so that's why I just put Randy Batubara there. I'm from National Research and Innovation Agency from Republic Indonesia. Today I will present about how to enhancing multi-level communication strategies in nuclear and radiological emergency preparedness and response. Okay. The effective communication during nuclear and radiological emergencies stands at the every core of a nation's preparedness and resilience. It is not simply an administrative function or a technical formality, rather it is a decisive element that shapes every dimension of emergency response, from the earliest situational assessment to the implementation of protective action in the field. So the integration of innovative technologies in emergency preparedness and response has the potential to revolutionize the safety and resilience of nuclear and radiological facilities, and explores the opportunities, lessons learned, and challenges associated with the implementing emergency preparedness and response technologies across various levels. And in high stakes environment where even minor delays or misunderstandings can amplify risks, the ability to convey accurate, timely, and comprehensible information becomes indispensable. Such communication determines how quickly emergency teams mobilize, how confidently authorities make decisions, and how calmly the public responds to unfolding events. The inherently complex and uncertain nature of nuclear incidents magnifies the importance of maintaining information that is both transparent and trustworthy, as misinformation or ambiguity can easily escalate public anxiety, hinder operational coordination, and erode societal trust in institutions. And therefore, position communication not as a supporting component, but as a strategic pillar that governs the coherence, efficiency, and overall effectiveness of nuclear and radiological emergency management. So in this opportunity, I will define 4 levels 4 levels. The first one is for nuclear facility, and the second level there's a nuclear zone. The third one is city or province, and the last one is national level. At the nuclear facility level, technologies such as automated monitoring system, advanced radiation detection, and predictive analytics are being implemented to improve real-time hazard detection, incident response, and internal communication. These innovation encounter challenges such as cybersecurity risks, difficulties in integrating with existing legacy system, and the necessity for custom solution tailored to specific facilities. The communication represents the most immediate and decisive link in the emergency management chains, shaping how quickly an incident is recognized, contained, and escalated to the higher authorities. As the first environment where abnormal conditions are detected, to the facility bears the responsibility of ensuring that the early signals of an emergency are translated into timely and accurate information. The facility must maintain redundant alert systems, secure channels for data sharing, and standardized communication templates that reduce ambiguity during the initial stage of an incident. Equally important is the facilities' preparedness to manage communication beyond its internal environment. And the second layer, at the nuclear zone level, where multiple facilities or critical infrastructures element may be concentrated, innovative technologies focus on enhancing situational awareness and coordination among neighboring entities. Geographic information systems are used to map hazards, while shared communication platforms facilitate quicker decision-making and more effective resources distribution. Major challenges at this level include ensuring interoperability between different organizations, managing data sharing policies, and aligning response protocols across various facility types and operators. At the third level, emergency response technologies at the city or province level are crucial for coordinating between nuclear facilities and local emergency services, such as fire safety officer, police, medical, and civil protection. Communication evolves into a broad outward-facing function that directly influence public safety, societal stability, and the overall effectiveness of the emergency response. Authorities at this level serve as the primary interface between a technical institution and the general population, translating complex radiological information into clear, actionable guidance that can be understood by communities of varying backgrounds. The success of their communication effort ultimately determines whether the public remains informed, cooperative, and resilient throughout the evolving pace of a nuclear or radiological emergency. At the last level, at the national level, technological innovations are essential for cohesive emergency preparedness and response strategies that align with international security, safety standard, and treaties. The communication becomes the central integrator that binds all layers that emergency response system into a unified and coherent framework. National authorities are responsible for consolidating information from nuclear facilities, nuclear zone units, and regional government, ensuring all methods disseminated to the public, media, and international partners are accurate, consistent, and strategically aligned. This level plays a crucial leadership role by providing authoritative authoritative situational assessment, clarifying uncertainties and addressing these discrepancies that may arise across different jurisdictions. Equally important is the coordination with international agencies, such as the International Atomic Energy Agencies and neighboring states, especially when the incident has potential transboundary implications. The stakeholders in the national level must also oversee the mobilization of specialized resources, including national radiation monitoring teams, medical response unit, military support for logistics, and national communication infrastructure. So, at the end, across these four levels, technologies emerge not only as an enabler, but as a critical point that reinforces the integrity of the entire communication architecture. Modern nuclear emergency management increasingly relies on a constellation of digital tools ranging from automated alert system and real-time radiation detection networks to integrated command and control platform and encrypted communication channels that allow information to flow swiftly and with a high level of accuracy. The communication emerges not simply as a technical function, but also a strategic instrument, one that integrates scientific accuracy, organizational coordination, and public engagement into a cohesive whole. The ability of a nation to respond effectively to a nuclear and radiological emergencies therefore rests not only on its technological capabilities or regulatory frameworks, but also on the strength, clarity, and consistency of its communication architecture. Thank you so much for the opportunity, and I want to say thank you for Riyadh and Saudi Arabia. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Randy. I want to introduce our next speaker and then invite her up to the podium. Our next speaker is from Turkey. It's Ms. Bahira Goptepe. She has a master's degree in nuclear reactor engineering from the University of London in the UK. She's a former nuclear attaché at the Turkish Permanent Mission to the IAEA in Vienna. She has an extensive experience in research, application, and the development of peaceful uses of nuclear energy. She currently serves as CEO of New Tech Energy and the president of Women in Nuclear, Turkey.
Thank you. Mr. Chairman, Madam Chair, ladies and gentlemen, good morning. It's a great pleasure and honor for me to address you all, the wonderful delegation of EPR 2025. I'm going to present to you our work, risk communication during nuclear and radiation disasters for newcomers. So this is a work I'm going to present to you a project. It is born naturally over the years as a result of work performed by the Women in Nuclear Turkey. These are the working people, scientists for universities and governments. We were doing a lot of environmental risk studies, post-Chernobyl projects, environmental risk assessment, and various projects on risk concern and risk perception and public concern. So over the years, all this accumulated knowledge become a shape of the NUCOM projects. Insights and gained and experience accumulated give us formulate such a project. And recently, with the natural disasters, unfortunately, big tragic earthquakes in Eastern Anatolia, we lost more than 50,000 people, and forest fires, which was happening in most of the places in the world, and floods, sort of shaped into a formalization of these NUCOM projects applied to natural disasters as well. So who are we? I'm presenting here, as the chairman introduced me, President of Women in Nuclear Turkey and CEO of Nutek Energy. What we are, the Women in Nuclear Turkey is a chapter of WIN Global, and our members are more than 200 now, and we are all working voluntarily in this network, and our main mission is to provide information to public on nuclear matters whenever is necessary to all the stakeholders. So our theme is nuclear is a green energy for peace, prosperity, and health in our country, in our region, and in the world. Republic of Turkey is a dynamic newcomer country. Our first nuclear power plant is under construction. It's called Akkuyu. It's the biggest nuclear construction site in the world now. More than 25,000 people are working. It's a unique project. It's handled as a cooperation between Turkish and Russian governments. And it's a model BOO, build, own, operate. And there are 4 units are under construction. It's a Generation 3 VVR nuclear power type. Well, I usually talk on behalf of women in nuclear. Why? Because in this field, in nuclear, we are highly educated in various fields, and no other career has no other job has this large spectrum, like safety and security and safeguard, environmental protection, radiation protection, communication, risk communication, and hazard protection. And women are always at the center of the energy matters in the world, and women are always more sensitive for a safe and secure world. So there is so much that I could say on the issue of communication with public and risk communication, but unfortunately in this very limited time, I could only say that effective communication with all stakeholders is one of the main vital issues for newcomer countries. And also, role of media is very important, especially if you are trying to plan nuclear power plants and you'll have to inform the public. Media is one of our main stakeholders. So why risk concern? Whatever we do, there are always people interested in the various questions and safety and security of MPPs, although safety, security, and safeguards are well-developed fields, as we all know. And while we were doing this work over the years, when I say this project, talking about project, there are 4 decades behind us. We've done a lot of work and tried to eliminate the causes, risk causes of public reaction. What are the causes, root causes of public concern on nuclear energy? It is usually the stories behind unforgettable stories of Hiroshima and Nagasaki, and also wrong correlation between nuclear armament and peaceful uses of nuclear power, role of popular media programs and films, and quality of media news is very important, and also trust or mistrust to technology and managers and administrators and politicians. If I had time, I would like to talk on this issue, which is very important, and also science fiction of nuclear horror films. There are many factors behind it. Well, bringing all together, I will try to describe you our work, what we call the NICOM project, on this flow chart. We use all sorts of communication tools, and usually what we were doing this work towards supporting Akkuyu MPP plans for our country. Turkey is a big country, and we planned nuclear power plants for several years, but they failed. So we were trying to support Akkuyu project during the normal time, providing information to our stakeholders. Main stakeholders is public and governmental authorities, municipalities, schools, universities, and all the other supply chain industries, even the risky persons. Under the normal conditions, it is very easy. You can tell all these stakeholders the benefits of nuclear energy. However, when there's an emergency, things become very difficult. What do you do as a risk communication? Under emergency, what sort of emergencies we had? Or we are in Turkey. Although we did not have nuclear power, we had this very serious emergency situation after Chernobyl. We were in the neighborhood. Although we were not really affected badly, it took us several years trying to sort out the problems. Turkey was badly hit, and we had the economic crisis due to our export of teas on the Black Sea coast, nuts, and many other goods. And I happen to be the project manager of one of the biggest IAEA technical cooperation project post-Chernobyl, marine environmental assessment of the Black Sea region. Not only Turkey, all the neighboring countries sharing the Black Sea coast, Turkey, Bulgaria, Romania, Ukraine, Russian Federation, and Georgia, all the scientific institutions, we worked together 7 years. It was a very hard work, sampling all the food and biota and sand and seawater and everything. Although the radioactivity levels were very low, it was very difficult to convince the public and some administrators. Of course, we also had the public risk communication after Fukushima. We also have some radiation incident, Ikitelli, where some radioactive source was handled by scrap metal labors. It happened to be a good story and very interesting analysis. And then recently, we had many other occasions like Zaporizhia, whether Zaporizhia may be a second Chernobyl. And then we have in our region, of course, this issue of Israel sending missiles to Iran, our neighboring country. So this, again, created a big public concern. Well, we had to act. And in these cases, as women in nuclear, we have been really very successful. Me taking part in the main media news and main TV channels. And it was really, we had very positive reflection. People would like to listen the stories from the experts. And then we had big earthquakes. As I said, in the Eastern Anatolia, more than 50,000 people died, and recent forest fires. So a lot of work for us on the risk concern. Okay. So all this accumulated work has given rise to another project, which called the RISCOM. Now in the Nutec Energy, we are preparing educational program on the risk communication and natural disasters including. So my conclusion is that risk communication and accumulated knowledge and sharing the knowledge between women in nuclear in newcomer countries are very important. And for newcomer countries, again, recognition of risk and public communication should be handled from the planning stage and should continue. And my last comment is, well, all the experience all in the world, not in Turkey, accumulated knowledge and insights gained on the some risk concerning public or all the world following radiation and nuclear accidents should be combined again under the new condition. What are the new conditions, developing conditions now? As I said, there are many newcomer countries online. Although nuclear technology is advancing very well, we are from 3 plus to 4, and technology in equipment and science is growing. We need more educated people, but we are under the most important threat of global change. Our ecosystem is under great danger, and plus we have the risk of military use in our region. So I want to finish my talk briefly, saying my theme for the women in nuclear, it should become a wish. Nuclear energy should be clean energy for the world, for more peaceful, more secure, more safe, and prosperity full of world, and for healthier world. So this is my wish, and I thank you to IAEA and our host country and all the organizer, and to you, all the listeners, and I wish you all the best. Thank you.
Thank you, Bahira, for sharing the perspective from Turkey. I'm going to introduce our next speaker and then invite her to the podium. Our next speaker is from Cuba. It's Ms. Marta Contreras. She's a nuclear energy engineer and a director of human capital at Cuba's Nuclear Energy and Advanced Technologies agencies. She has abundant experience over 20 years in communication and public opinion research on nuclear issues, and she leads Cuba's communication group for nuclear emergencies. Marta.
Good morning, everybody. I'd like to say thanks to IAEA and the organizer here. It's a privilege for me to be here. My presentation is Communication in Radiological Emergencies based on audience research. First, a brief presentation about my country, Republic of Cuba. Cuba is an island in the Caribbean Sea. We don't have nuclear power plant, not research reactor, so radiological hazards are use or ionizing radiation source, existence of nuclear power plants in neighboring countries, and navigation of nuclear powered vessels in waters close to the country. National authority and coordination. The National Civil Defense Headquarters is the national authority in charge of organizing, directing, executing, and controlling the application of the policy for reduction of any type of disaster, including radiological emergencies. Civil defense has a strategy for disseminating civil defense measures for disaster reduction and has a public communication plan for radiological emergencies in Cuba. So communication is a vital line of work. Civil defense leads crisis response, but how to translate technical complexity into the public message. So, Minister of Science, Technology and Environment, through the Office of Environment Regulation and Safety, providing technical advice to civil defense, and Nuclear Energy and Advanced Technology Agency is part of the structure as the main institution promoting nuclear application in Cuba. This structure has a communication group. His mission is to transform radiological data into comprehensive alert and concrete actions for the population. This is a picture about a plan. Cuba nuclear power plant emerged in 1918, with 5 directions: nuclear energy, nuclear techniques, basic and applied research, radiological protection and nuclear safety, and training of specialists. Supported, all of them, supported by scientific information and communication. But an effective communication needs to know motivation, perception, needs to the audience. So during 30 years, we studied, we researched about this time. The question is how Cuba transformed 30 years of audience research into a communication strategy to save life. I try to answer this question right now. In 1990s, the first research was about acceptance. One question about a system of conditions for the application of nuclear energy in Cuba among journalists and executives. This is the sample, or worst example. The majority of sample say yes. Question about information provided about nuclear energy, the majority of sample says insufficient. And the other results, 100% of journalists and executives agree with the use of nuclear energy in Cuba as long as established safety and protection standards were met. In 2004, 2006, research was about attitude. The relevant results, the information provided in the country on the use of nuclear techniques is insufficient. The 98% of respondents agree with the use of nuclear energy as long as established safety and protection standards were met. These results were presented in the International Conference on Knowledge Management in Vienna in 2007. In 2008, 2012, we investigated with research about perception among executive, journalists, expert, client, user. Executive says spending on communication is an investment, but communication is not based on scheduled action. Journalist says they are unaware of scientific results from nuclear center and claim there is a little communication with them. Expert says image of nuclear activity is positive and communication should be worked on with a well-designed strategy. Client, users, expert, and journalist says little dissemination of nuclear activities in the country. The most valued aspect was human resource. These results were presented in the International Conference on Human Resources in United Arab Emirates in 2010. In 2016 to 2016, the diagnosis of communication in radiological emergencies must shows strengths and weaknesses. Strength, clearly defined structure with assignment responsibilities. Extensive experience in responding to national disaster, and there is a group responsible for communication. And weaknesses, insufficient general knowledge of the population regarding radiological emergencies, limited use of social media and the internet, no mechanism has been defined for detection, monitoring, and control of rumor or false information. This is my recognition to the team for 30 years. Team have psychologists, sociologists, and communicator. How did this knowledge shape Cuba's communication plan? Well, technical recommendations used by IAEA are implemented and adapted to the national process for reducing risk of disaster. Action for the preparation and response to radiological emergency establishes in national plan are complemented and strengthened. It contributes to Cuban national security in his disaster risk reduction dimension through communication with the public in response to radiological emergency. What is the pillar of communication plan? Education, instruction, simulation or exercise, communication during the emergency, and communication to reduce psychological and physiological effects during and after the emergency. This picture, the right, shows a group in the exercise Combat E2G in February this year, organized by the IAEA. These exercises are very important for us. Lessons learned. What can we learn from Cuban experience? Continuous audience studies equal to realistic plan. Media are force multipliers if training before crisis. Trust is built through technical transparency. We never say no risk. We say these are the levels and immediate action. This aligns our model with IAEA standard, but with a plus, the Caribbean cultural factor. Finally, we say in Cuba, we do not improvise alerts. We design them with 30 years of social data. But the main message, the principal message, evidence-based communication of social research is a vital as dosimeter and hazmat suite. Thank you very much.
Oh, very good. Thank you, Marta, for sharing with us the Cuba perspective. I would like to now introduce our next speaker and invite him to the stage, to the podium. Our next speaker is Ali Jida. He's the Assistant Head of Emergency Preparedness and Response Division at the Nigerian Regulatory Authority. He has more than 18 years of experience in regulatory inspections, national emergency planning, and he participates in IEA peer reviews. Ali?
Thank you very much for the introduction. Good morning, good afternoon, good evening, all seated here, and those joining us virtually around the globe. So my presentation will examine how Nigeria handles public communication during nuclear and radiological emergency, the different channels of communications, the law enforcement agencies and organizations that are involved, as well as the use of different channels of communication. So the goals of this presentation is to share lessons for strengthening policy coordination in emergency communication. This is just an overview of the country. Nigeria is located in the west coast of Africa. It has a population of 223 million smart, intelligent, hardworking, hospitable Nigerians. Nigeria appears to be the largest population in Africa and the top oil producer in Africa and the 6th exporter of oil and gas in the world. Currently, we don't have nuclear power plants, but we have a research reactor. It's a miniature neutron source reactor, 31 kilowatt neutron research reactor that is operating. But Nigerian government has made commitments to include nuclear energy in its energy mix. So by way of introduction, we know that communication saves lives. But what type of communication are we talking about? We are talking of communication that saves more life. These are communications that are timely, transparent, concise, unambiguous, trusted, all put together forms what is called effective communication because it minimizes panic, foster public trust, and prevent misinformation, misinterpretation, and confusion. So the legal basis for emergency communication in Nigeria stems from the Nuclear Safety and Radiation Protection Act 19 of 1995 that establishes the Nigerian Nuclear Regulatory Authority with the prime responsibility for nuclear safety and radiological protection regulation and emergency response in the country. That is to say, the NNRA is the sole competent authority that has that mandate. Put together, the National Emergency Management Agency, in cooperation with the NNRA, together with the relevant stakeholders, developed as enshrined and as empowered by the law to develop the National Response Plan for response to nuclear and radiological emergencies. All these are in line with international best practices. In terms of leadership and coordination structures, Nigeria follows the all-hazard approach. That is to say, nuclear and radiological response is integrated in the National Disaster Response Framework, while NEMA, being the national coordinating body, coordinates all emergencies at the federal level, at the state level, and at the local government level. And just like I said, the NNRA is the competent authority that has responsibility for nuclear safety, radiological protection, and emergency in the country. Other agencies include the Nigerian Atomic Energy Agency, the Radiation Research Institute, which include the Center for Energy Research and Training, Center for Energy Research and Development, Nigerian Institute of Research, Radiation Protection and Research. Then we also have the health authorities, like the National Center for Disease Control and Prevention, security forces, which include the Security and Civil Defense Corps, the Nigerian Police, the Nigerian Army, the Nigerian Navy, the Nigerian Air Force, as well as other international organizations, civil society organizations, non-governmental organizations, all have their roles being defined in the National Response Plan. This is the off-site communication structure. It is an horizontal and vertical coordination and communication for emergency management. In case of any emergency within a facility or in a facility, the first response is from the licensee or from the facility. The response is in terms of notification and communication. It communicates with the off-site emergency response organization, which is a prerequisite and a requirement as mandated by the regulatory body to have an arrangement with the off-site emergency response organization as part of its emergency arrangement. And notify the authority, the competent authority, which is the NNRA, on any incidents or emergency regarding nuclear or radiological emergency. And the NNRA, being the competent authority, is the only authority in this case that has the authority to communicate with the IEA if the need be. And if there is need to activate the National Emergency Response Plan, the NNRA communicates with the National Emergency Agency that has the sole authority for coordinating all responses, all emergencies, all disasters in the country. This National Emergency Management Agency has its own offices at the zonal offices, the state offices, the local government offices that communicates with the community. And this is the National Nuclear and Radiological Communication Strategy. The NNRA has the responsibility to conduct hazard assessment. Down there are the elements that forms the communication strategy. With respect to public communication, Nigerian public communication strategy, owing to the population of Nigeria, over 230 million smart, intelligent, hardworking, loving, and hospitable Nigerians, leverage on all the available media channels because of the population, because we want information and communication to go around the length and breadth of the country. This includes the mass media, the digital, social media, traditional media, which involve town criers, using the mosques and churches, announcement, as well as community meetings. These are areas that don't have internet, areas that the literacy level is very low, and no TVs, no radios. So we use the traditional method in order to disseminate information timely, accurately, and in a trust pattern. And looking at the diverse culture of Nigeria, we have over 500 languages. And it will be very difficult to communicate in all the languages. So we have 3 major languages in Nigeria. These are Hausa, Yoruba, and Igbo. Not forgetting that the official means of communication or language of communication in Nigeria is English. But these are the 3 major languages, the Hausas from the north, the Yoruba from the west, and the Igbo from the south. So all messages are translated and developed in these languages. And to substitute this, communications are also done in the local dialect of those particular areas. In terms of media engagement protocols, the Nigerian strategic plan mandates proactive media outreach, which includes press conferences, media workshops, training for spokespersons, trainings for journalists, as well as education and awareness to the public. These particular actions highlighted the importance of communications to the grassroots. And the IEA-IRS mission highlighted this practice as a very good practice during the IRS peer review mission. And with respect to joint information system, this is on a case-by-case basis. So this is just one example that shows Nigeria in action in terms of communication, timely and effective communication, multi-agency collaborations, as well as public engagement. This is an incident that involved a missing radioactive sources, which is cesium-137. Despite the fact that all the transport arrangements were in place, which include having armed security forces to escort movement of radioactive sources, the transportation route, as well as requirement like moving from 6 a.m., between 6 a.m. and 6 p.m., and as well as areas of stopovers. So the driver stopped over, and when he returns back to the vehicle, the container was missing. And the next thing was to alert the facility that the container was missing. And the facility immediately notified the NNRA. And the NNRA, after verifying the true status of the incident, notified the International Atomic Energy Agency through the illicit trafficking database. As of then, now it is incident trafficking database. And after all search and done, the source were recovered in Germany. But what later followed is the consequences. The facility was shut down from operation for a good 2 years. The facility operation license was retrieved, and the facility was fined with a huge sum of money to act as a deterrence to negligence. So this actually demonstrated effective communication, public warning, and multi-agency collaboration that helped to manage the incident. So some of the challenges is the over-reliance of response organizations, stakeholders, media, and the public on the NNRA matters related to nuclear and radiological emergencies. Well, we all believe that there is low media and public interest in nuclear and radiological matters and misconception about radiation by stakeholders, media, and the public. Despite the coordinated response, there are still some challenges with respect to inconsistency in coordination among agencies. And again, response organization relies solely on the National Response Plan, for which each agency is expected to develop their SOPs, but they rely on their conventional response or communication plan. So some of the lessons learned from Nigerian experience is the integration of nuclear and radiological emergencies and response into the National Disaster Response Framework, as well as the use of multi-channel, culturally sensitive approach. because of the diverse nature and the population of the country. So my recommendation with respect to legacy and policy is to finalize the policies and the laws, because these policies and laws have been reviewed in order to be in line with the international best practices, as well as some of the IEA's review documents that were used as the basis or references for developing these documents. And there should be a continuous routine media press briefing and workshops, local languages materials, and also to partner with the National Orientation Agency in Nigeria. And Nigeria is also, through the NNR, is also making effort to have a dedicated code for communication with the NNRA and notification to the NNR regarding nuclear or radiological emergency. Instead of using individual phones or some dedicated phones, we want to have like a national code. So in conclusion, Nigerian experience shows that integrated nuclear and radiological response or activities into the National Disaster Response Framework it has built a solid foundation for public communication during radiological and nuclear emergencies. And the use of multi-channels means of communication is a very good practice, because one size does not fit all. And one channel, the use of one channel is not enough. So public communication is not an afterthought, but a critical component of nuclear and radiological emergency. So in conclusion, thank you very much for listening.
Thank you, Ali, for sharing the Nigeria perspective with us. I'd like to introduce the next speaker and then invite him to the podium. Our next speaker is from the United States Nuclear Regulatory Commission, Dr. Todd Smith. Dr. Todd Smith is a senior level advisor for emergency preparedness and response at the US NRC. He provides strategic and technical advice on emergency preparedness policy, and he has published extensively on radiation risk perception and crisis communication. Todd.
Good morning. In 1938, as Americans turned on their radio after dinner, their programs were interrupted by a startling report. Martians had invaded the Earth. The War of the Worlds radio drama by Orson Welles was widely reported in the newspapers to have created widespread hysteria and fear across the nation, resulting in mass evacuations. Following the event, researchers tried to understand, how could a radio drama create such mass panic? But is that what really happened? It wasn't until recently that new historical research into the events revealed that much of the reported hysteria is what we would call today fake news. No, the public did not believe that aliens had invaded the Earth and were attacking our cities. In the context at the time, most people were concerned that the conflict in Europe had reached American shores. They thought it was a human war. Yes, a few people were fooled, but they immediately realized it was a hoax and they laughed it off. In the radio studios, Orson Welles and his broadcast team were surprised when officials showed up because of concerns of public panic. And yet, as Orson Welles would later remark, when he left the studio the next morning, he was surprised to find that everything was normal. Life went on. And yet, the event became a cultural phenomena, and myths of the event of that day continued for generations. In 1979, as Americans turned on their television after breakfast, the programs were interrupted by a startling report. The 3 Mile Island nuclear plant had suffered a meltdown. The accident at 3 Mile Island was widely reported to have created fear, confusion, and panic. But is that what really happened? Yes, there was a lot of anxiety, but a lot of that was due to conflicting reports of the event. In the context of the time, this public confusion was amplified because Hollywood had just released a movie about a fictitious nuclear meltdown. Most people just didn't know what to expect. And when you look at local reports, we see a different story. Many of the locals were not afraid. Locals even put up signs telling reporters to turn around. There was no story. And local newspapers began to report stories of weddings and other events continuing in the midst of the emergency. For many people, life went on. And yet, the research from the time seemed to tell a different story. It seemed to suggest that nuclear power was the most dreaded fear on the planet. But is that what this data is really telling us? Have you ever looked into this data? I can tell you that the respondents was a very narrow demographic from a very small part of the country with a very anti-nuclear bias. If you look at other public surveys from the time, including respondents to this survey as well, you find that most people believed nuclear power was safe. And yet, the event became a cultural phenomena, and the myth grew that the public was afraid of radiation and nuclear power. But the myth does not stand up to the data. In the United States, public support for nuclear power only continues to grow. When you look at surveys of American fears, you find that nuclear accidents are no more dreaded than accidents of other types or natural disasters. And recently, our states who are interested in nuclear power began surveying their public, and what they find is the public doesn't know anything about this new technology. And yet, surprisingly, they believe it's safe, and that new nuclear technology is even more safe. And yet, the myth persists. We have this cultural bias. When you ask people, are you in favor of nuclear power, they often answer in the affirmative, yes. But ask them, what do you think your neighbor thinks of it? And the numbers go down. This is a particular bias known as pluralistic ignorance. And we see examples of it everywhere. For example, a few years ago, our Department of Energy asked the public, what do you think are the 3 biggest hurdles toward deploying nuclear energy? And the responses were public perception, ignorance, fear, fear, fear. And yet, later on, when they asked the public, what do you think of nuclear energy? The responses were very simple: clean, reliable, safe. The trouble comes for us in risk communication when we begin to believe the myth. What I'm showing you here is a figure that we use in training on psychological aspects of radiological emergencies. The figure is showing you psychological phases of recovery following emergency events. The yellow line are non-radiological emergencies. The white is radiation. The image gives a clear message. Radiation emergencies are different. They are not. Radiation is a unique hazard, as all hazards are unique. But it's not different. We know this in part because at the NRC, we studied the non-radiological health effects of evacuations and relocations from all types of emergencies, and we found that radiation events do not produce outsized results. But another reason I know this isn't true is because when you look into this figure, the yellow line has a published source. There was an actual study of the psychological phase of recovery. The white line for radiation has no data source. It is simply a reflection of the myths, of the fear that we continue to believe that somehow radiation is different. And so you see, the root cause of our problem is that effective barriers to risk communication start with us, not the public. And I'm not the first one to suggest this. More than 20 years ago, Theodore Rockwell said, it's hard to get the public to believe your assurances of safety if you insist on terrifying messages to the contrary. But I'm here to tell you we can change, and I want to show you next how we changed. It started by rethinking our beliefs of what the public believed. At one point, our risk communicators thought it's challenging to talk to the public about radiation. You can't even use the word radiation without them thinking they're immediately going to die. Well, we tested that. We did some message testing with the public, and what we found, they do understand radiation. And they understand not all exposure is harmful. There's low doses, and then there's high doses to be concerned about. More importantly, what the public understood is that there's effective steps we can take to protect ourselves from radiation. So we rethought our beliefs about protection. At one point, our risk communicators thought it's just going to be too difficult to advise people. They're just not going to believe that we can take effective steps for protection. So we challenged that. One thing we know from all hazards crisis and risk communication is that the public seldomly acts irrational in time of emergency. When emergencies happen, we go into an information-seeking mode, and we know we need to give complete information to decision makers and the public. So we went back and tested the messages, the information we want to give the public, and the feedback we got was very interesting. The information our risk communicators thought the public would be interested in, the public had no interest in. The public didn't care how many bananas it takes to have some kind of equivalent dose. They wanted to know one thing. What do you want me to do to be safe? So we changed our message. No longer do we talk about no safe dose. We made it very clear which levels are safe and which levels are not safe. And then we changed our beliefs about preparedness. At one time, our risk communicators had concern that we couldn't take an all-hazards approach to radiation. We still had to treat it differently. They didn't think we could use simple heuristics like stop, drop, and roll like we do in fire emergencies. And yet we can. We have a very clear, simple message. Get inside, stay tuned. Why does this work? The nature of emergency is uncertainty. And in times of uncertainty, people rely on habit, and going inside and sheltering is a habit people know and trust. What I just shared with you is how we changed our culture. But let me walk you through the process in a little more detail. In her book, Thinking in an Emergency, Elaine Scarry notes the key to change is through deliberation, good governance, and good habit. You can see in the examples I provided, it started with deliberation, thinking. We challenged our beliefs. We changed our biases. We did surveys. We gathered information. And then we asked ourselves, what are the habits we need to have in place to assure public protection? And we put those into place, and then we updated our risk communication to match those habits. Linking deliberation and habit is good governance. And this is the critical role that the U.S. Nuclear Regulatory Commission plays. Our risk-informed regulatory framework is what enables us to connect our thinking to our habit, our science to our state of practice. At the NRC, we talk a lot about what it means to be a risk-informed regulator, and it's more than just how we write our regulation. It's not just something you proceduralize. It is a cultural shift. It's a transformation in how we meet our safety and security mission for the future. And that future is here. The technology is ready, the public is ready, so we need to get ready as well. So together, let's change our risk communication culture for public health and safety. Thank you.
Thank you, Dr. Todd Smith, for that perspective. Our last speaker for today is Sophie Delecom from the IAEA. Sophie's resume was so long that it would take the whole session for me to read it out. But in short, she's the director of the Office of Public Information and Communication since 2019. She has over 20 years experience in strategic communication, crisis management, advocacy, and public relations. In this field, Sophie has done so much of practical work across various international issues. And it's very impressive. Sophie, I'll introduce you now.
Thank you, Gino. Salam alaikum. Good morning, everyone. Ladies and gentlemen, excellencies, all protocol observed. I'm the last speaker, so I'm the one standing between you and a delicious lunch. I will try to be rapid and entertaining like the previous speakers. So, let's dip in the slides. Okay. If you have to retain only one thing from what I will say, this is what you should retain. Can you help me? Okay, the green, yeah. Yes. So, trust is not a message, it's a partnership. I repeat, that's the most important message. Trust is not a message. It's a partnership. It is built during normal times, and it is tested during emergencies. So how does that work? At the IAEA, we have principles when we communicate. Those principles are a systematic dynamic. Speed, transparency, and accuracy. This is the first dynamic. We have to be rapid. We have to be transparent, but it has to be accurate. Neutrality, objectivity, authority. We are the IAEA. And as the IAEA, we have to make sure we are still impartial and neutral during crisis. This is very important. But how to have the speed, transparency, and accuracy? It's also through consistency, reliability, and accessibility. Accessibility, very important. Spokesperson, CEOs have always to be ready to answer interviews. You have to understand the media, they will not wait for tomorrow. They will need the information immediately. Two examples of what we did, for example, for the Fukushima HALPS release, the treated water release, we created a real-time monitoring web page. What you see on the screen, it says active because right now there is a release and we are capturing real-time sensors information from the TEPCO nuclear power plant, and it is accessible to the public, researchers, media, immediately on our website, during night, during day, with the time difference. The next one is the timeline, reference material documentations, always accessible to the public and the media. You go to the website and you find them immediately. Disinformation. It was mentioned a little bit. It's a threat multiplier. So the facts. During emergencies, disinformation is deliberate, it's highly targeted, and it undermines technical facts with emotional narrative. So what are the consequences? It really erodes compliance with safety and instructions, it amplifies panic, and it polarizes the public discourse. So, policy implication, what can we do about it? We have to do it at the policy level. One very important aspect is to institutionalize rapid communication protocol. Why to do that? We can't have the same clearance system of normal times. We have to have speed clearance of communication content before it is released. Organized media training. It was also mentioned by a previous speaker. Media journalists have to be trained. Every media in your country needs to have at least 2 journalists trained. So you create a network of specialized journalists that knows what is what and who to call when there is an emergency. You need also to elevate disinformation at a national risk assessment level. This is also super important. If it's not at that level, then it will not be considered in all your different risk assessment mechanisms. Interoperability of AI. I will speak a little bit of AI right after, and what is important when you're using different tools is that they are interoperable. And the last but not least, you need to establish ethical, legal frameworks for the use of AI. It has to have strong safeguards and also human accountability. So, one dive into how AI can help us. Open source intelligence for real-time tracking with digital threat mapping. The tools of AI right now are really giving us a lot of possibilities. We have the mapping of the disinformation and the tracking of geolocalization of where is it coming from, how is it spreading. You can identify the affected areas, you can identify the blind spot where the communities are also raising attention. You can detect the panic by the search words. If people are looking for evacuation, if people are looking for radiation symptoms, you can identify really by the word that are searched what are the concerns of the population in specific areas. And you can provide verified data to create the communication that is required. So, practical examples. First example, real-time disinformation tracking. One scenario, there is a bot that is creating false information about the level of radiation and how it spreads. So what we can do is know exactly where it is coming from, as I mentioned, know exactly what are the communities, what they think about what is there, and so you can target your message to answer in real time what is the concern of the people and diffuse the panic, diffuse the risk and the misperception. Second quick example, how to prepare an interview. Super useful for journalists, super useful for spokesperson, communication experts. You can have, before an interview, a mapping also of the trends, the concerns, and then tailor your answer, the Q&As, based on what you need the population to be clarified on. That's a very important point. Also to equip with visualized data and impactful message. Our brains retain message in an emotional way. Not just we think, but we feel. And with AI, you can capture those very impactful messages that people will memorize. Third example. Let's say we have on X the campaign that is saying radiation is beyond the reality. So it's changing in real time. So how can we do that? We can have real-time sentiment analysis. Who is positive, who is negative, who is neutral. We can really assess which messages are impactful, how some are disengaged from those messages, and we can adjust the tone, the content, and the timing. With infographics, with videos. There is a lot of different tools that are out there, and I invite you to ask the question during the question and answer time. I will not give you example right now, but you can ask me about it. And then there is tools also for dissemination, automatic dissemination, choosing the right platform for the right message for the right audience. Another thing that is interesting with AI is what you can find on the AI for Good platform. It's the ITU, which is a UN organization that is collecting all those documents, and I invite you to visit their website. There is a lot of publications that already exist and that have been published quite some time ago, like the one from UNESCO on the ethics of AI, the UN activities on AI from 2022, or generative AI in jobs from ILO, etc. and etc. The AI for Good platforms is really a goldmine of information if you want to search for standards, for example, or governance. In summary, the main message you remember is trust is a relationship. It's not a message. You have to build it with the media, you have to build it with the public, and there is a different trend now. Before people go to website, now our analysis has demonstrated people go to social media. They don't go to website anymore. So you have to make sure you have a very important presence on social media with different platforms targeting your different audiences. It's also a way to help the one-on-one communication. You don't have to go through the media, but you have to build this relationship with the media. The efficiency principle, this is also something that to keep in mind also every time you communicate during normal times, but also and especially during emergencies. Work at the policy level. Don't forget to elevate at the policy level everything you want to do and achieve on communication, so you standardize it. Use digital threat mapping. This is very important. AI is here to be used, to be mastered with safeguards and ethical protocols. And finally, you have to identify, train your people, and deploy those practical tools, making sure they are interoperable. Thank you very much.
Yeah. Thank you, Sophie. I also want to thank the audience for leaning in and being so attentive. I'm going to flip the script a bit. You know, normally the chairperson asks the panelists questions, but I'm not going to do that. I want to give you the opportunity to ask any of the panelists questions around their presentations. So I'm going to invite you as the audience. I know Rahul is waiting to ask a question. So yeah, please, if you'd like, there's one, two, I see two people at the back. Could you take a roving microphone? Yes.
Thank you for such an amazing presentation from all the panelists. I'm Nasai from Malaysia. I would like to pose a question to any of the panelists who want to answer this question. If you have the chance to redefine the entire system of emergency communication for nuclear system, what kind of fundamental principle would you change, and why do you think the world hasn't adopted it yet?
Okay, thanks. Did you get that question?
It's difficult to hear.
Was this for Sophie from the IAEA?
Anyone.
No, it's anyone, they said.
For anyone. Sophie, you want to take that?
I haven't heard very much the question.
Todd, do you want to take that? Or anyone? I think, would you mind repeating the question? There is a slight echo in the room, so it's probably getting muffled.
Okay. If you had the chance to redesign the entire nuclear emergency communication system from scratch, what fundamental principle would you change, and why do you think the world hasn't adopted it yet?
One thing I can say about that is shift the mindset between being reactive to being proactive. That's the main important thing. We tend to react of what is happening. We have to be proactive. Everything has to be prepared in advance. You have to have everyone trained, and so you have all built a relationship, and you're proactive instead of reactive.
Yeah, that's one answer. And to add on to that, I think all the role players need to look at it differently. Communicating during an emergency should not be a traditional PR exercise. It's slightly more serious than that. So there's a mind shift that needs to take place. There's a culture shift. There's a system shift. So the whole landscape needs to shift. Not everywhere, but in some countries. The second question, please.
Thank you so much for the wonderful presentation. My name is Lorna Ungayo from Kenya. I'm a radiation safety officer. I work in a nuclear medicine facility. The experience we have encountered when it comes to communication to the patient, specifically radiation risks, already the patients, they have perception, and even they think that this radiation, it's going to do more harm than the benefit. So you find that we used to experience, because nuclear medicine is new in our country, we used to experience patients, they come, we book them, then they disappear because they fear that it's going to do more harm. And when we started the initiative of explaining the benefits that are associated with it, the greatest challenge we were experiencing is they are asking us how safe it is. So trying to explain with this patient in technical language, it's a bit tough. What they want to ask is how safe it is. So my question is there a way we can quantify the radiation side effect or risks, the way we have, we can quantify the earthquake? When you are told it's the magnitude of 5.3, you already have an idea. Is there a way we can quantify the radiation risk to simplify it to the members of the public, and it is knowledgeable to them? Then it is easier for them to be able to know how these risks is associated with it. Thank you.
Does anyone want to take? Yep. Dr. Tond?
Yeah, there's an easy way to quantify it. It's safe. I think what you need to look at is the experience which a lot of our countries have on communicating radiation treatments to patients. And a lot of the experience seems to be that no matter how much we try to quantify or make comparisons, that's not the information they're looking for. So I would look into what is the message that will resonate with the individual and build your program from that.
Thank you, Todd. We have a question here and a question there. So on the second row and the first row. I think to add on to what Todd is saying, you won't get a straightforward answer here, but he touched on it from a very high level. The how part is what you're looking for, and the how part we need a further engagement on.
Good afternoon, dear panelists. My name is Mirjana Čović. I'm from Serbia, Vinča Institute of Nuclear Sciences. I have a question maybe for you, Sophie. I don't know, are you familiar with Safecast organization? That organization established after a Fukushima accident occurred, and immediately after the accident, there was no any information about those rates. And then a group of people combined together and built a very simple device with a Geiger tube, some GPS electronics. They combine all that together and start to drive and to measure those immediately near the accident place. And then they share all their data on the mobile phone. So so actually, first data that occur about those for general public arised from that Safecast organization. So in critical emergency situation, how much society and general population can be helpful, and I want to hear about that from your side. Thank you.
Thank you. So it's a double-edged sword, right? There is what the population can do, what the NGOs present on the ground can do, but there is what the nuclear operators, the nuclear regulators, the civil protection are mandated to do. And so I think it is, again, going back to building a partnership between those organizations and those that are mandated and authoritative voice to make sure they don't contradict themselves, to make sure they build the trust together. Because what we need is not to polarize with different numbers, different perspective. We really need to be a conjunction of messages and things to be aligned. This is super important for this trust that we're trying to build during normal times and also during emergencies.
Sure, thank you for that. It's a long process to build that trust. We'll take the last question.
Yeah, I have to apologize to the audience and the panelists for the fact that I'm delaying your lunch, so I'll be really quick. When I started this business decades ago, and even today, nothing goes out to the media until it's been reviewed and approved by some senior manager. The reason is you don't want to put out wrong information. You want to make sure it's coordinated. In today's age of social media, we don't have the luxury of time. It has to go out really, really quick. How do you do that without losing the coordination with the other organizations and without losing the control on the veracity of the information you have?
That's a very challenging question. Anyone want to take?
Practice.
Yes.
Practice and prepare. We develop those messages ahead of time with templates, ones we know are good, and we set them up for the stages of the emergency we know we'll be dealing with, and so we can rapidly respond in time of emergency.
It's about those rapid communication protocol I mentioned. You have to have agreement at all levels that in case of emergencies, this is the clearance mechanism. Who clears what and when? And practice really helps. We have the experience at the IAEA with the situation in Ukraine, where we're having those DG statements very quickly being posted from our spokesperson who is drafting the first draft. Then it goes to the director Deputy Director General of the department, and then the special senior advisors of the DG, and then the DG. So it's really quick. It can take a couple of hours, sometimes when people are traveling a little more, but sometimes we have to answer in 30 minutes. So what we do is we couple the press statement with social media posts. And then we have one that is very short, that is giving our position, and then we go more into details with a press release.
Yeah, I think, the reality is that because of the rapid spread of information across these channels, you'll find that sometimes authorities, role players are catching up. But the important thing is that you got to build credibility before an event takes place. So if you're an authoritative voice, the public tends to look for the authoritative voice. It's not an easy question, and we can't really answer it. It's something we need to catch up with. But yeah, coming back to that, first, let me thank the audience for giving up your time, for investing your time to listen to the session. I want to thank our speakers from different countries for sharing their talks. And I also want to let you know that these presentations will be available on the IEA website. It is just a soundbite, a snippet. It's not the how-to, but it is there to stimulate your thinking. And when you go back to your respective organizations in your regions, I think you can prioritize communications during an emergency. Last but not least, I want to thank Nayana Jayarajan for putting together the program and for bringing us all together. The session is officially concluded. Thank you. You want a photograph of the team?
Ladies and gentlemen, distinguished guests, session will start in 5 minutes. Ladies and gentlemen, distinguished guests, session will start in 5 minutes. Ladies and gentlemen, please find your seat. We are starting shortly. Ladies.
Distinguished delegates, ladies and gentlemen, again, I hope your lunch was as delicious as I found it. The food here I will absolutely bring with me as a fond memory, for sure. We are on day 4, which means keynote number 4. Today we have Mr. Jing Chuning. He is the General Manager of the China Nuclear Power Engineering Company. He's in charge of the design and research work for nuclear power plants in China, including HRP-1000, ACP-100, and advanced reactors. He's experienced in safety evaluation, emergency preparedness and response, and site selection, to name a few. So please help me welcome to the stage Mr. Jing Chuning.
Thank you very much. Your Excellencies, distinguished guests, dear colleagues, good afternoon. My name is Jing Chuning from the China Nuclear Power Engineering Corporation. I've been working for the nuclear industry for 30 years, 12 years in the Design Institute, and 18 years as an EPC contractor for the nuclear power plant. In recent years, I also involved in SMR in Chinese project. Actually, in China, we have a high temperature gas cooling reactor, 2 units actually in North China. 2 years ago, we put in commercial operation. Currently, we are constructing PWR SMR in South China. We're just doing the hot functional test. And within 6 months, we will finish the construction work and commissioning work. And in the middle of 2026, the ACP-100 will put into commercial operation. Besides these reactors, we also have program for the mobile reactors. For example, the land-based macro reactors on the track. So also we have the floating reactors on the sea. So it's a great honor for me to share some information and opinions regarding the EPR for the SMRs. As emergency preparedness and response professionals, we are seeing the rapid changes in nuclear technology, especially with the land-based, mobile, and floating small modular reactors. At the same time, no matter how advanced these reactors become, emergency preparedness and planning zones will always need to be considered. This is not about promoting any one technology. It is about keep people safe. So we have to answer the question, why emergency preparedness still matters? These days, we have heard about many innovative nuclear technologies. They are changing the way we think about emergencies. With new designs, smart systems, and better communication tools, we are moving from the passive defense to active resilience, anticipating risks and strengthening readiness before incident occur. Yet, even as we improve efficiency and reduce costs, our responsibility to plan for the emergencies remains the same. Safety standards must never be lowered. So what we have to keep in mind is the safety first. There is no exception. Every new reactor design must be checked using both the deterministic safety criteria and the probabilistic safety analysis. Safety criteria are the basic safety rules to be followed, and the PSA shows what could go wrong and how likely it is. Both the approaches are important in the SMR safety evaluation. Both approaches is very important. In some countries, for example, in my country, in China, small reactors are now required to demonstrate even higher level of the public protection than large reactors, often by remaining safe and self-sufficient without relying on the external power or emergency support. One of the reasons is to use the scenario. The use scenario of SMR is more complex. We need to consider more about than before, such as the heat and the steam supply, seawater desalination, and of course the power supply. They all have different end users. Sometimes the consideration and the requirement are very different. So many people may wonder, what is SMR and what is different? The SMRs are designed to be safe. They have smaller reactor cores, large thermal inertance, and other advanced design features. The radioactive release during accident of SMRs can be reduced. Their parts are built to avoid larger accident. For example, SMRs typically adopt the integrated pressure vessel and no large diameter primary loops, primary pipes, which are normal in the traditional large reactors. Their design can eliminate some of the initiating events, like the main pipe break, reducing the possibility of emergencies. They use the gravity and the natural circulation for cooling, so they don't necessarily need external power. And the passive design reduces the risk of equipment failure or human error. Meanwhile, some SMRs adopt accident-tolerant fuel, we call it ATF. The ATF can enhance the fuel tolerance under accident, providing more time for the accident mitigation measures and reducing the radioactive release. That is to say, their fuel is made to handle emergencies better. Such features can make the drafting of emergency plan simpler, but it's impossible to eliminate the severe accident with much lower residual risks. So we have to consider the proper EPZs preparedness which are commensurate with the safety level from the conservative perspective. In other words, we still need to plan for the equipment failure, multi-modular failure, and the human error, and the unexpected scenarios. So the point of EPR is to plan for the unplannable and expect the unexpected. Even with safer reactors, the EPZs are still needed. Multiple reactors together means we need to plan for the problems that could affect all of them because they normally share the systems, for example, the cooling or heat sink or electrical grid, and so on. And that is to say, we need to ensure the emergency plan to consider the accident scenarios due to the common cause failure. The mobile reactors will need plans for emergency that can occur during the transportation. In this case, the emergency preparedness need to consider the traffic risks and at the same time the external disaster risk. Even more, it requires making the real-time risk assessment during movement. For floating reactors, we are facing the risk from storms, ship collision, and the spread of radioactive material in the sea. They also face the difficulty in deploying a fixed monitoring network across the marine area. We need to enhance the capability for monitoring and assessing the coupled marine and atmospheric environment, which is very difficult. Consider both of the meteorological factors and operating status of the floating platform and ensure the effective protection and the response in a complex and changing environment, the marine environment. Different authorities might be responsible for such an accident from those who are responsible on land, for example, such as the Coast Guard, Coastal Administration, and the Search and Rescue Departments. They also need information, training, and exercise, and ensure these authorities and responsibilities are clearly understood and specified in the emergency plan. Reactors near cities or facilities can create new types of emergencies, like the traffic jam or chemical accidents. The short distance between nuclear and chemical facilities that can easily form a hazard source cluster effect. So we need to have the capability to respond not only to nuclear, but also to the chemical accidents. Nearby facilities also need training on what to do for the emergency declaration at an SMR. There may be some arrangement between the SMR and the nearby industrial facilities. We have the high temperature cooling reactor supply the steam for the chemical factories. So this case, we need to both consider the nuclear and the chemical accidents. The SMRs can make the emergency response easier in some ways. Perhaps they will need fewer people and less equipment, but maybe their emergency facilities can be smaller. However, how this will need to look still need to be developed together in such an international forum like today's conference, the IAEA EPR2025. This is a very good platform for the professionals, regulatory people, and the experts to exchange information, share the experience and expertise. And thanks a lot to the agency, the IAEA and the Kingdom of Saudi Arabia, host a very successful and wonderful conference. Since these reactors need to the electricity production, heating, desalination, cleaning water, and so on, the EPR community must be ready for the new and different type of emergencies, including compound and complex emergencies. So our EPR system need to be more effective, more smart, and more accurate. We still face many challenges. The rules and standards for these new reactors are still evolving. Most are still based on the graded approach applied for the large reactors. Standards for SMR regarding licensing, emergency preparedness, and multi-use application are not yet fully developed. We need new ways to analyze risk and plan the safety zones using the flexible and site-specific methods, including all steps through the extent analysis, atmospheric dispersion to the dose assessment, and also the evaluation of the protection actions. These reactors are more complex, so the emergency team need more training and must work together across different areas, such as nuclear physics, thermohydraulics, and material science. It requires a lot on the technical comprehension and cooperation across different areas. The people sometimes think the small reactors are less risky just because they are smaller. But the safety depends on design, not the size. So we need better ways to explain the risk to the public. For this, we need to use a graded approach in the EPR. Let's talk about the floating reactor. They also bring new challenges. We must think about both the nuclear safety and the ship safety. The weather at the sea can spread radioactive material farther than on land. We also need to think on how to predict this and make good dispersion models and be able to measure and follow it. From this, the emergency plan should include ways to communicate with each other, with the challenges of the sea and the airports, and we need to find ways to work with different governments, locally, nationally, and internationally. Getting help for a reactor far from the land can be very difficult. So cooperation between the relevant authorities, perhaps possible self-rescue and technical support systems will also be important. There are many new technologies. These days, we've heard about of the AI, the smart system, robots, and for new ways to send information. They are changing how we respond to emergencies. The AI can help us spot risks and make decisions faster. This must, however, always be double-checked by us humans. The AI technology can build an emergency decision-making model by analyzing the multi-data, including the historical records and the real-time monitoring information. And for example, it can help the decision-making system rapidly to generate optimal protective action plan by using the unmanned vehicle for radiation monitoring, and make the emergency drills from the tabletop access to a virtual reality drill to enhance the emergency response capability. But what we need to pay attention is the accuracy of this AI decision is highly rely on the quality and the integrity of the training data. This is a crucial issue for the AI application of the AI tools. Robots can do dangerous jobs, like the checking for radiation or cleaning up. The application of advanced communication technology can enhance the accuracy and the robot action during the emergency, such as the remote operation and real-time data transmission. Sometimes we use the quantum communication. It's a new and very secure way to send information. In the short terms, it means the message can't be easily intercepted or tampered with, so the emergency team can trust the information they get. Again, with the checkpoints put in place to ensure the security of the information. Ladies and gentlemen, dear colleagues, we have to work together globally for the better use of these technologies. And as these reactors are used in many countries, it's important to work together and share knowledge. The IAEA helps the member countries set standards, share experience, use the new technology to improve the emergency response, strengthen the emergency framework, and promote globally standardization. Many new nuclear technologies and other innovative technologies are changing the nuclear emergency framework from the passive defense to the active resilience, which also bring some new challenges. But no matter how much nuclear technology changes, the emergency preparedness and the EPZs will always be needed. Our job is to make sure that we are ready for any emergencies, keep people safe, and never cut corners on safety. That's all for my keynote speech. Thank you for your attention. Thank you very much.
Thank you very much, Mr. Cheng. So now we are over to the final roundtable. That was a very inspiring keynote for EPR for emerging technologies, including small modular reactors and beyond. And the next theme is following up on that, emergency preparedness and response for floating and mobile reactors. Going into emerging challenges and the role of the graded approach. Our moderator for this session is Ms. Marina Demeshko. She's a nuclear safety specialist at OECD NEA, and she has been that since 2018. She manages the Multinational Design Evaluation Program and its working groups, including LWSSMR. Ms. Demeshko has almost 20 years of experience in nuclear research, engineering, safety, and regulation. She also has a PhD in engineering. So I'd like to welcome the panel to the stage. And while they're on their way up, I'd just like to mention that the hard work of the technical officer is by Agnieszka from the agency. Whoops, careful.
Good afternoon, everyone. Welcome to our session dedicated to the challenges on emergency preparedness and response for floating, mobile, and land-based small modular reactors. I'm looking forward to our discussion and to insights from our distinguished guests, and it's my pleasure to introduce them to you. So first is Mr. Todd Smith. He is Senior Level Advisor for Emergency Preparedness and Response from NRC USA. Todd Smith is the Senior Level Advisor for Emergency Preparedness and Response at a Nuclear Regulatory Commission. He provides expert technical advice for development of emergency preparedness policy and guides performance of research to advance the state of the practice in radiological emergency preparedness and response. He graduated from Purdue University with their master's and PhD in nuclear engineering, specializing in thermal hydraulics and reactor safety, and holds a master's in radiation health physics from Oregon State University. Dr. Smith is an active member in the Health Physics Society, American Nuclear Society, and Society for Risk Analysis. Our next guest is Mr. Kyowon Choi. the Senior Nuclear Safety Inspector at Department of Emergency Preparedness of Korea Institute of Nuclear Safety, South Korea. Mr. Kwon is a senior inspector with over a decade of experience in charge of EPR oversight program and rulemaking for SMRs. Prior to that, he served as a chemistry manager at Korea Hydro and Nuclear Power Company. He represents Korea at the IAEA EPR-SC and NEA WP NEM. He holds a master's in nuclear science and technology from the University of Manchester. Our next speaker is Ms. Nadezhda Salnikova from Rosatom Russian Federation. Ms. Nadezhda Salnikova is a strategic project lead with more than 10 years experience driving complex international projects in high-stakes, heavily regulated environments. Having a master's degree in international studies and technical background in nuclear energy and technical physics, Nadezhda has ensured development of business model and operation concept for the nuclear floating power units to be operated in multiple jurisdictions. Nadezhda is a member of the IAEA Technical Working Group on small and medium-sized or modular reactors. And the next speaker is Mr. Per Inge Orstand. He is a senior advisor in the Emergency Preparedness and Response Department of the Norwegian Radiation Protection Authority, DSA, in Norway. Per Inge started at the Officer Candidate School in 1977. His service in the armed forces has mostly been with the Combat Engineers, and he was commandant of the Combat Engineers Center of Expertise. He became commandant of the Norwegian Joint CBRN Center of Expertise in 2007 and held the position until 2019. He has since 2020 worked as senior advisor in the Emergency Preparedness and Response Department of the Norwegian Radiation Protection Authority. And our last speaker is Mr. Guilherme Dionísio Alves. He is a deputy secretary at Brazilian Office of Naval Nuclear Regulation in Brazil. He is a senior engineer with master science degree in mechanical engineering. In the last 10 years, Mr. Alves been working with complex programs involving technical knowledge in naval and nuclear fields. Nowadays, he is the deputy secretary of the Brazilian Office of Naval Nuclear Regulation, managing the development of the regulatory framework for floating nuclear power plants, considering nuclear safety, security, and safeguards. Nice to see you here. So let's be back to our session. As the keynotes mentioned, the SMR technologies are advancing very rapidly, with more than 80 designs under development and projects moving forward across China, Argentina, Canada, Russia, South Korea, United States, several European countries, and other countries. There is a wide variety of the application of the SMRs, and they are opening the new possibilities for flexible low-carbon energy. Yet, as technology evolves, so must our approach to emergency preparedness and response. Even with enhanced safety features and smaller source storms, EPR remains the critical final layer of defense in depth. And today, we have a unique opportunity to shape how EPR frameworks will adapt to these new reactor configurations. One of the key challenges is that our global safety framework was built around fixed location facilities. To ensure robust preparedness for floating and mobile reactors, we must account for the realities and complexities of the maritime environment. And I hope we will be able to discuss in more details these issues today. So I will be going back to the questions, and I will start first with Todd. Can you please share how can regulators and technical support organizations ensure that EPR requirements evolve in step with innovation while maintaining a consistent level of safety?
Thanks for that question, Maria. It's a great question to start this panel off with. I think I want to start with the end of that question about the consistent level of safety. In the US, the NRC, we have a standard of adequate protection of public health and safety. And with that standard, it's the same thing we consistently apply to all of our licensees. But because each of those technologies is different, we apply a different approach. So we take a graded approach to the different technologies. And a graded approach can be illustrated in this way. Let's take a different hazard. Let's think of water, and let's take the risk of drowning. then what we do to manage that risk looks different if I'm on a cruise ship, or a small boat, or at a pool. In each case, it's the same hazard, but the risk is a little different. So what I need to do to manage the risk looks different. But note that my safety objective is the same: protect people from drowning. And that example gives us an idea of what we may be looking for in how we regulate. How can we achieve flexible regulation by maintaining the same safety objective? And the answer is a performance-based approach. What we do in performance-based regulation is specify a measurable safety outcome without getting into the details of how you achieve that method. And so performance-based regulations, like we have implemented for alternative emergency preparedness regulations for small modular reactors, non-light water reactors, other new technologies, is a very useful approach to keeping up with innovation, to inspire continuous improvement, and to maintain a consistent level of safety. Another key to that is to be also technology inclusive in our language that we use. When we approach regulation, understanding there's so many different new designs, we want to avoid technology-specific terms, especially those that may cause issues in emergency preparedness and response. An example that always comes to my mind, I think about a molten salt reactor. And it would be very interesting if we were in a situation where there was an event and somebody asked, is the fuel melted? He said, yes, because that's the natural state for that reactor. So by being technology inclusive also in our regulation, it helps us also to find clear, consistent ways of communicating in crisis and emergency.
Thank you, Todd. That was a very comprehensive answer. My next question will be to Per Inge. How are regulators aligning their approaches to emergency preparedness and response for SMRs across different jurisdictions in case of floating and transportable SMRs?
Well, there are key points to address this question. Collaboration and cooperation. It means that operating floating mobile SMR in transboundary environments requiring strengthening international coordination and harmonization to ensure an effective response to nuclear emergency. Organizations such IAEA, IMO, member states, classification societies, and some important non-governmental organizations like NEMO have to work together in order to harmonize emergency preparedness requirements across their jurisdictions. It is important also to not forget to include in this process the State Maritime Authority and the Port Authority. Going to the international instruments, there are existing ones. The Convention on Advanced Notification of Nuclear Accidents is an example, but they should be updated or supplemented for floating SMR. Second, EPR harmonized standards. And there is a very interesting reflection. Since from the beginning, the nuclear regulatory framework was built considering the principle of a fixed location. And this does not work properly with floating SMR. And this is exactly the case. We should adapt the technical documentation, the framework for floating SMR. We can think about, for example, regional coordination mechanisms. For example, regional centers for emergency notification and response, especially in areas where the maritime traffic is heavy. We can think about also in the creation of cooperation protocols between coastal neighboring countries, especially in emergency notification and risk communication. Some of these coastal countries lack of nuclear infrastructure. Another important thing is we have to harmonize the regulatory framework. Generally speaking, there are the measures we can have done.
Thank you, Guillermo. You see, that's a very interesting and very complex issue of the harmonization of regulatory approaches and international mechanism across jurisdictions. So I would like also to ask Per Inge to share his opinion on this issue.
Yeah. Nuclear powered vessels today are operated by states with competent authorities providing regulations and guidance, and economic muscles ensuring proper production, use and termination. Floating and transportable SMRs will most likely be in service as propellant for large commercial vessels in the near future. New commercial SMR-driven vessels will be operated by large companies that have the economic muscles necessary to ensure safe operations and will operate them according to international law and the regulations given by the nation who operate visited ports. Today, the operator or owner of a vessel will normally change during the lifetime of a vessel, and there are examples that vessels are operated beyond their expected lifetime due to commercial and financial interests. For these vessels, it happens that over time, highly qualified crews are replaced by lower qualified crews due to financial reasons. In such situations, there is an increased risk for unwanted and unexpected incidents. Regulators should therefore ensure that both international and national laws and regulations ensure proper operation and EPR throughout the expected lifetime and probably beyond for new SMR-driven vessels. The regulation should cover all relevant aspects, and functional areas and special attention should be on requirements for proper competence and manning throughout the estimated shelf life of for both the SMR and the vessel itself. It should not be a surprise that the future will bring a situation where an operator will try to extend the shelf life of the reactor or vessel to an extent where the risk for unwanted incidents will increase. Regulations should therefore provide clear guidance on requirements for possible extended shelf life. International law on free passage in international waters ensures international economic growth, but also provides challenges in respect to support to or intervention in emergencies. Within territorial waters, which is limited to 12 nautical miles or about 22 from the coastline, the respective country do have legal right to intervene in an emergency in order to prevent or support an emergency. In international waters, a prerequisite for any support from a neighboring nation is that the captain of the vessel asks for support. And these challenges are today a concern, especially for transports with dangerous goods, but will likely be relevant in the future for SMR-driven vessels. Thank you.
Thank you, Per Inge. And since today we have a chance to hear the first-hand experience of the first modern floating nuclear power plant, I would like to ask Nadezhda, what approaches are used today in Russia to manage EPR issues with regard to floating power units and nuclear icebreakers?
I would like to start a bit with the background, because the first icebreaker was initially put into operation in 1959, and today we have 9 icebreakers in operation with advanced reactors, of course, and the main difference between the icebreaker and the floating nuclear power plant, FNPP, is that the icebreaker is used for propulsion, for movement, and the floating nuclear power plant is expected to be transported with the reactor in a shutdown condition. But the technology is pretty the same. And as for regulation, the approaches of GSR Part 7 and GSR Part 4 are pretty applicable. We have the same in our national regulation, but of course well developed according to specific sea events. And what makes the major difference from land-based is the approaches to safety assessment and EPRs, because we should take into account not only the site, but also the shipyard where the vessel is constructed and fueled, and then the route from the shipyard to the site, and then the route from the site to the service facility where the maintenance is conducted. So, when at sea, the floating nuclear power plant or the icebreaker should be able, the crew of this vessel should be able to deal with any kind of accident without any help from the shore, at least at the initial stage. Of course, we have some specific events like pitching and rolling and possibility of clash with the other ship and even turnover, but in each accident there should be proved that no releases is possible, and even if it is proved, we should have a specific emergency plan on ship. And when the ship enters into port, it should be perfectly integrated into the emergency system of the port itself. Here it is important that not every port can be entered by the nuclear ship. In Russia, we do have a special list of such kind of ports, and they all have to meet some specific requirements, like having monitoring system, having a special pier for nuclear ships, and also having some procedures established, like the speed of entering into port, the route of entering into port. And what's more, all ports have their specific geographical weather conditions. It is analyzed when we are dealing with preparing emergency procedures. And of course, the issue of integration is one of the most important. So it's basically the approach we use in Russia for this issue.
Thank you, Nadezhda. And what lessons from the academic Lomonosov and other first-of-the-kind projects can guide the refinement of international guidance for floating and mobile SMRs?
Lots of, and basically not only academic Lomonosov, but also the icebreakers, because they're passing through territorial waters of other countries. And it's important that the international society also doesn't start from the scratch in this issue. In 1968, there was a document on safety considerations for the ports entered by nuclear ships. This document was developed by the IEA and IMO. We also have some provisions on nuclear ships in the UN Convention on the Law of the Sea and the Convention on Safety of Life at Sea, and also a special code for nuclear ships. And all those documents were initially developed in the beginning of the era of nuclear ships, like Autogun, Savannah, first icebreakers, and they're pretty old. But combining the experience we have today with this regulatory basis, we can move to a modern regulation, quite transparent, for the FNPPs to become worldwide without compromising safety. And the important step was made by IMO this year. We have received an approval of the proposal to update the code of nuclear merchant ships. So this work will be done from the next year.
Thank you, Nadezhda, very inspiring. So we will move a bit away from floating and come to the land-based SMRs. And I would like to ask Kyuwon, what are the unique safety assessment considerations for multi-module or grouped SMR facilities compared with a single reactor unit? And how should emergency planning zones be defined or optimized for grouped SMRs with smaller inventories, but potentially cumulative risks in the rare multi-unit events?
Thank you, Marina. I think this question is kind of most frequently asked question these days around the world. But in addition to the common challenges associated with multi-unit accidents from conventional nuclear power plant sites, there are several pre-identified unique challenges associated with multi-module accidents from the SMR site that can include some independence of critical safety functions or potential impact on safe operation of perhaps other intact modules from an event if there's an event on an adjacent modules. So that makes the SMR sites more like a conventional nuclear power plant-ish. So that would be the problem. But in fact, sizing an EPZ, it's in light of multi-module accident risks, this question can becomes really simple or either an easy question if we just acknowledge that EPZ was originally developed as a planning tool. So we must look back the rationale behind the determination of the EPZ. So determination of the EPZ was actually based on the full spectrum of accidents, so considering the corresponding consequences tempered by probability considerations. So a common misunderstanding viewing the EPZ is as a design feature or unsafe zone or even a blast radius. And this kind of misunderstanding leads people to ask what the ultimate or absolute distance for immersive planning should be, right? So technically, if we ask this kind of question, I think it can never be answered until we just expand our EPZ to the national borders or either covers the entire Earth. So while the EPZ certainly considers that those distance relations analysis, considering the range of the accidents, but the other key function of the EPZ is to provide a substantial base for expansion of emergent response should it become necessary, right? So again, this is not a new concept or new approach to only apply to SMR. It has always been there. So sizing an EPZ for SMR is just simple. We are just applying the existing approach to SMR, considering their spectrum of accidents.
Thank you, Kawon. Well, another challenge for the land-based SMRs is that they will be probably next to the densely populated area. So I have a question to Per Inge. Should the early warning, evacuation, and public communication strategies be adapted for densely populated regions hosting innovative reactors, and how?
Thank you. SMRs may be located in areas with various populations. A regulatory body or a governmental issued license for establishing of an SMR will use the risk and threat assessments from the responsible operator or owner as some of the fundamentals for the licensing process. The risk and threat assessments address relevant current topics such as infrastructure and population and the short-term planned development of the region. At the same time, the estimated shelf life of an SMR will vary, but may be 40 to 50 years. And the given shelf life may also be extended, which we see examples of from traditional nuclear power plants today. An SMR may be critical as an energy source in an area, and its presence will provide new possibilities for both industry and population. This may cause that what initially was a densely populated area over time is transformed to something else. It is therefore important that the risk and threat assessments take this into account and are revised in a systematic way, ensuring that an adjusted environment is addressed and properly managed in respect to EPR. SMRs are new technologies, and the presence of these is something our populations are not used to. Therefore, there will be a strong need for both the information to and communication with the public both close to and in the vicinity of new SMRs. It's important that the public are given the possibilities to raise questions and get answers so that their needs for information is taken care of. Many are in general skeptical to new technologies and their possible safety challenges, and there are examples where this has proven to be right. Those skeptical will also focus on information that supports their skepticism. It's therefore important that information to the public from both the regulatory body, other authorities, and the facility owner or operator addresses both the advantages and disadvantages, possible emergency situations, and how the public should act in these circumstances should also be addressed. The information should be clear, using language and terms the public understand, and to the extent possible, be presented by someone who has public trust. The amount of people either working or living close to an SMR should not determine the content of the information provided to the public. Anyone in the public who is made aware of a situation or has to act in an emergency will need both upfront and current information. We should also be aware of the information needs of those who has their loved ones close to the location. The threat and risk analyzer should be living documents that are regularly updated, addressing any substantial change in the environment close to the SMRs. Systems for early warning, evacuation, and public communication must be adaptable to environmental changes in the lifetime of the SMR. Thank you.
Thank you, Per Inge. I have a question to Todd. There have been mentioned graded approach several times. So can you explain if the graded approach allows for reduced source term modeling requirements for very small reactors, or does mobility and transport introduce new complexities that require more detailed modeling?
Another great question. And I think one thing with the graded approach, it is a flexible way of approaching these different designs, the complexities, and then figuring out how we apply it to emergency preparedness. One thing that's really been impressed on me this week, when you mentioned source term in Q1, you talked about the spectrum of accidents. Yeah. I think one thing that maybe we didn't talk about enough this week is the importance of that source term information. It is the basis for how we begin preparing, what are the capabilities that we need. It forms the foundation for our tools, like our dose prognosis, so we get reliable, accurate results, and it helps inform our decision making. And I was just reflecting too on our opening session with the reflections on what we learned in the past from Chernobyl and Fukushima. And we don't want to have to learn from experience. We want to think ahead, what can go wrong, and how do we prepare for that. And the source terms are so important for that. And we're fortunate that we've come a long way with source terms. In the past, we used bounding assumptions with a lot of conservatism in that. And how that impacts emergency preparedness is that in the past, we tended to take precautionary approaches. And as we've talked about this week, those can lead to doing more harm than good. Now, with mechanistic source terms, with tools like probabilistic risk assessment, we can apply those source terms in new ways to reveal new risk insights that can help us better inform protection strategies to protect the public. And it's interesting when you mentioned to the complexities of the different environments and situations we're going to find ourselves in. This is the same question we've been having in the US. How do we deal with this technology and that technology and that technology? And we usually start off in the same spot. Well, what's the source term? What does this look like? Until we realize, wait a minute. We're still just dealing with radiation. We've known about radiation since 1895. We know more about radiation than almost any other hazard. And importantly, we know how to protect ourselves from it. So a lot of our discussion has been, while the technology may be getting more complex or the environment's different, maybe what we need to be thinking about in EP is getting back to the basics. What are the things we do well? What are the things we know how to do that protect the public health and safety? Now, source terms still play a big part in that. One of the things that we're doing at the NRC is saying, well, let's look at representative, say, microreactors, mobile microreactors. What if we look at a bounding source term and we say, what does that look like? And what we find is that looks like this radiological event over here or that one over here. And by making those comparisons, it does two things for us. One, it helps us to be an efficient and effective regulator because we understand that in terms of the radiation hazard, we've seen this situation before. And the other thing that it helps with is it gives assurance to our response community that they have the capabilities, that they have the tools, that they have the training, that the people to go into an unknown situation, but recognize they still know how to deal with the emergency.
Thank you, Todd. That's quite a clear guidance for such a complex issue. I will be back then to Kyowon and ask him to share his opinion how regulators and industrial parties can work together to create a common understanding of the graded approach in EPR to diverse SMR design.
So I think for all of us, I think the most important thing is we should understand the point of this question. So we all agree that immersive planning is a matter of defense in-depth level 5. So our focus should be on more of a risk profile, not rather than a facility type or technical advancement of certain technologies. So planning standards and immersive preparedness oversight program was developed in most countries to ensure adequate immersive planning capabilities exist. So it has always been risk informed in a way. So historically and practically, they're always risk informed. But unfortunately, legal system and regulatory requirements to operators or licenses were developed in a prescriptive way, mostly based on the studies or analysis done by national level. So currently, at current stage for the existing and conventional nuclear facilities, most countries' experience is mainly focused on how we just require them prescriptive requirements to ensure EP capabilities exist. But this reminds me of ongoing discussions at IAEA APROSC meetings regarding the need for revising the Table 1 of the GSO Part 7 or Table 6 of GSG 2.1. So it includes the immersive preparedness categories. So these immersive preparedness categories, the concept of it is actually based on risk profiles. So to provide requirements or recommendations to member states, IAEA used this term EPC based on the risk profile for providing them graded requirements. But many interested parties or stakeholders, they focus on the supplemental examples provided in those tables, such as nuclear power plants, such as research reactors. So for us, at this moment, the important first step would be a clear understanding on the label SMR does not automatically trigger graded requirements to be applied, but it begins a journey to understand the risk profiles of the diverse designs and different types of offsite consequences, so which will be the base of the immersive planning. So,
Thank you, Kiron.
Yes.
So my next question will be to Nadezhda. What unique technical or logistical considerations arise for emergency preparedness in floating or mobile reactor designs compared to land-based units? What kind of coordination is required between the supplier state and the host state?
I really like the idea put on the table by Todd about the necessary conservatism. And the idea that now we know more about what could happen in nuclear than before. But we should take into account not only the nuclear part, but also the sea part. That's why, because when making safety assessment, we also analyze a lot of information about the sea navigation, sea observations, and all this, the history of accidents that could happen at sea. And this both is quite a large package to be analyzed, but it should be done in order to prove safety and be ready for anything that could come. And as for the cooperation between different states, it's always tricky because of interfaces. Under the UN Convention on the Law of the Sea, it is the state of the flag of the vessel that is responsible for the safety on board. It means the supply state. And then the ship enters into a port. It is the host state that is responsible for the safety of the port, including the safety of the ship. So we face here the overlap of jurisdiction, and we have to define clearly who is responsible for what. So the responsibility of parties should be clearly defined. And from the technical point of view, the point is in communication channels that should be clearly established again and synchronized in order to be ready to any kind of response. And again, here we can learn a lot from maritime, because they have centuries of experience of large ships entering into port, ships with dangerous goods and even dangerous ships in accident conditions entering into ports. And we should absorb this best practices in order to move forward.
Thank you, Nadezhda. And my question next is to Guilherme. While developing a comprehensive regulatory framework for naval and floating nuclear systems, what guiding principles are shaping this process?
Yeah, thank you. The Brazilian Office of Naval Nuclear Regulation is working very, very hard in order to develop a regulatory framework, considering an integrated approach between nuclear and naval requirements. For example, safety analyses are to be developed for every naval system that may induce a nuclear risk. And, as I said before, safety and security have to be considered not only for the floating reactor, but also for the host port. Otherwise, we won't succeed. Going to the guiding principles. The first one, safety and security are absolute priorities and have to be considered during all the floating reactor life cycle. Safety requirements can focus first, keep the nuclear reaction under control, to remove the residual heat and to establish an adequate shielding for safety. We have to use the concept of defense in depth for security in order to avoid incidents or nuclear accidents. Number two, international cooperation and transparency. We have to consider that the float SMR can operate in international waters or in exclusive economic zones, requiring international cooperation. And it's really important that to be completely transparent with the coastal neighboring countries that can be affected by an incident or a nuclear accident. Number three, we have two sets of framework, the nuclear framework and the maritime framework. Imagine if these two sets of frameworks addressing the same subject differently. Probably it will be a big mess, and we won't succeed. In this regard, we have to put nuclear regulatory framework in the same page of the maritime law, especially the United Nations Convention on Law at Sea and SOLAS. And this document will be reviewed next year inside IMO, International Convention for Safety of Life at Sea, especially Chapter 8. Number four, when we move a reactor from land to the ocean, it means that we are changing static scenarios, static threats by dynamic scenarios, dynamic threats. As I said before, in the ocean we have storm, waves, swells, and safety has to deal with this. From the security point of view, we have dynamic threats. Please imagine the following scenario. A floating reactor fully loaded of fuel. I'm sure that this scenario will scare too much the IAEA safeguards experts. How to deal with it, how to avoid misuse of sensitive nuclear material. We have to deal with it. Another important point, liability. As I said before also, who is in charge of what? During the licensing process, we have different players. We have the designer, the ship designer, we have the shipyard builder, we have the reactor designer, we have the reactor producer, we have the ship owner, we have the flag country. In case of an incident or accident, especially in international waters, who is in charge of what? We have to address this question. And we have also to consider that as possible as we can, it is really important to harmonize the standards and to have a regulatory cooperation, because at the end of the day, what we want is to move a floating reactor from the point A to the point B, whatever in the ocean. Other important point, Todd has said something about graded approach, and I will try to go a little beyond. Regulators can use the risk-based approach. Why? Because normally, floating reactors differ significantly from the traditional reactors in terms of technology, in terms of size, in terms of power, and it's important to understand this difference and try to apply this difference in the licensing process. So the conclusion to close this question is, in fact, we have to realize that there is too much work to do, everybody of us. Thank you.
Thank you, Guilherme. So that was very interesting to share that it's very important to realize who's responsible for what. And for this issue, I would like to ask Per Inge, what unique response capabilities or command structures are needed to manage emergencies involving floating or mobile reactors in maritime environments?
Thank you. Mobile and floating SMRs gives us new challenges in respect to emergency planning and response, even though nuclear-driven vessels, such as icebreakers, have been in service for decades. Floating and SMR-driven vessels may be divided in three categories in respect to EPR. Those permanently located within the territorial waters of a state, those sailing between and visiting harbors, and those sailing in international waters. Floating nuclear power plants permanently located in territorial waters will operate according to national regulations and are under the supervision of the state regulatory body. The state will have a national system for emergency preparedness and response where roles, responsibility, and tasks are defined and addressed for both national, regional, and local authorities and emergency capabilities. For visits to a national port by a nuclear-driven vessel, nations have different licensing procedures and EPR arrangements. As an example, I will shortly explain the Norwegian system and procedures for visits of allied military nuclear-driven vessels. Roles, responsibilities, and EPR tasks regarding licensing are regulated by a binding document available in Norwegian and English on the regulatory body webpage. The Commanding General of the Norwegian Armed Forces is formal host for the visit and responsible for security and safety, and that the emergency plans are coordinated with civilian authorities, first responders, and rescue services. Ports for visits are predefined, and for ports, civil-military EPR arrangements are defined and in place based upon the risk and threat documents. When a vessel asks for permission for a visit, the armed forces will ask the regulatory body for an assessment on safety for the specific visit, and the regulatory body will consider and if found acceptable, recommend to the Ministry of Defense that the license should be granted by the Ministry. As of today, national regulations on a formal process for visits by civilian SMR-driven vessels are not in place, but it may be something similar, as described, but with other authorities in charge than the armed forces. For nuclear-powered vessels in international waters, it's more complex in respect to emergency planning and response. The law of the sea ensures free passage in international waters and is a prerequisite for international trade. It's likely that there will be no exception on this for commercial nuclear-driven vessels. In respect to EPR, this provides challenges. An example is a nuclear-driven vessel that faces technical problems in bad weather, not far away from the territorial waters of a nation. The captain of the vessel is the one who decides if there is a need for rescue or other kind of support, and he will then request assistance. The captain's judgment might be that external support is not necessary, while the nation close by may make other conclusions. In such situation, the possibilities for the territorial water nation is limited in the legal respect to a kindly request, as long as the vessel is in international waters, since the legal framework for forced interventions is limited to vessels within the territorial waters. Thank you.
Thank you, Per Inge. As it was mentioned several times during this conference, even when you have a very clear command structures, communication is the key. So my next question is to Todd. While the strategies used to foster effective communication and coordination among operators, regulators, first responders, and the public during the public during an emergency at large NPP be different from those for SMRs and for floating or mobile?
The question is, do the communication strategies need to be different because the technologies are different?
Yes.
So one thing I've really picked up on a lot this week is the importance of the communication, coordination, and the cooperation that happens. Just in the last session, the IAEA brought about the importance of trust and how that's built on relationship. And actually, just at lunch, I was discussing with Sarah Miller about with communication strategies, the principles are the same. They're universal. They haven't changed. So this is a good thing because we have a strong foundation for how to approach this for these new technologies. We just need to apply it. And this is the other thing that was been impressed on me in this week, is I think about what we need to do to prepare our communities. I realize that it's time to put the past in the past. Chernobyl, Fukushima, we acknowledge them, we learned from those events, but that was our past. That's not our future. And so what we need to be doing is focusing on that future. If you remember Dr. Leake's keynote speech, she was talking about the future looking about these multi-hazard events. And that's, I think, where we really need to focus our energies to prepare our communities. What is it going to look like if you have a community with a small modular reactor and a few micro-reactors, and there's a wildfire coming through that community? We have to develop those relationships early on, develop the trust, so that when the nuclear plant is telling the emergency manager, I'm safe, we have it covered, or these are the resources we need, they know what is needed. And this is also very important to make sure that the resources, which are going to be limited, as she mentioned, get allocated in the right ways to ensure public health and safety. So I think that communication, coordination, cooperation is going to be key. But the good news is we have a very strong foundation and principles that will help us apply it.
Thank you, Todd, and thank you for mentioning all hazards method. I would like then to go deeper into site-specific hazards and have a question to Nadezhda. What are the challenges in developing site-specific hazards assessments for SMRs intended to be deployed in remote or infrastructure-poor environments?
The main challenge here is the fact that we have only one design that should be stable, even at site, and then at route. So we should take into account not only site-specific hazards, but also those hazards that can be at the root, at sea, far away from shore, or at any stage of the life cycle. And again, we use the maritime statistics for external hazards, and we use the statistics of our own to develop the deterministic scenarios of what could happen inside the sea, inside the vessel. We are frequently asked about even we consider such kind of thing like turnovers and clashes and possible icing. Yes, we do. Anything that could happen at sea is considered, and there are two possible ways to deal with that. Even we have safety systems to deal with such kind of accident, or we can somehow exclude the possibility of such event in the life cycle. For example, there are no Aframax type ships, large ships, in the Northern Sea route. So it is not necessary to consider such an event when the floating nuclear power plant clashes with this type of ships. They just do not go there. It is a kind of organizational measures that can help us to exclude this type of event. But all the other events that could happen are considered. And that's why our safety assessment is quite large. And we have even a list of events developed by our regulator that must be considered within safety assessment. And again, this list is also used for developing the emergency system and emergency planning.
Thank you, Nadezhda. I have then a bit different question to Guillermo. Can you please share what are challenges to manage the interface between nuclear safety, security, and non-proliferation when regulating floating nuclear power plants?
Yeah, thank you very much for the question. Yeah, normally the big issues are in the interfaces. And when we consider safety, security, and safeguards, to summarize, the big challenge is to develop a framework in a balanced and consistent manner, considering the 3S, safeguard, security, and safety, security, and safeguards. Let's try to address these things. Safety requires transparency, technical access, and international cooperation. Security requires secrecy, control access, and protection against threats. Safeguards requires protection in order to avoid misuse of sensitive nuclear material. The challenge is a measure in one area does not compromise the effectiveness of other area. In other words, some measures in the safety area cannot compromise safeguards. How can we manage this? This is one challenge. The second, I would say that due to the mobile and transboundary environments for floating SMR, the challenge is to apply, to guarantee that safety, security, and safeguards will be similarly in all the locations, even considering that the floating SMR is in international waters. In this case, we can think about, for example, of an international register under IAEA, for example, real-time location of the floating SMR, for example. Third challenge, in the licensing process, as we discussed before, we have different players. The shipbuilder, let's say. We have to guarantee that safety, security, and safeguards will be applied and be effective in all the phases of the floating SMR life cycle. It means during the design, okay, during the construction, during the operation, during the maintenance, wherever it happens, the commissioning, especially in the operation, wherever the floating SMR is. This is a big challenge, and we will face how difficult it is to manage the interfaces. And also, we have different regulators in all over the world. We have to consider that these regulators have to apply in a balanced way these principles. So, Mariana, generally speaking, these are the main challenges in managing the interface between safety, security, and safeguards.
Thank you, Guillermo. And there's even more and more challenges to discuss, but unfortunately we don't have much time. So I would like to ask the audience if you have any questions to our experts. There are a couple.
Shiran from Jordan. Actually, I would like to focus on the emergency planning zone for SMR. It was well addressed in the dialogue, and I'm very satisfied to hear many questions I was planning to ask. But in this moment, I'm presenting a research on the sizing for EPZ for SMRs to enable the feasibility for the non-electric application of SMRs, such as refineries, water desalination, and hydrogen production. So in my research, which is presenting outside on the screens now, I found the biggest challenge is the regulatory issue and the licensability for reducing or optimizing the emergency planning zone. So my question is, who's responsible to initiate this work? It's always the owner-operator, I know, who's the applicant initiate this work, but in our case, for the developing country, it will be very difficult for the regulator to do this work if it's not being approved in the country of origin of the SMR. Thank you.
Thank you. Who would like to answer?
Well, I think certainly it is up to the regulator in the individual country to set the standard for the safety for the EPR arrangements, including emergency planning zones, and that is certainly the case in the United States. Now, how does it work among the regulator, the licensee, and the planning committees? It's a very cooperative arrangement. We set the standard, and then the licensee has to demonstrate how they meet that standard. Now, what's interesting, you talked about a particular challenge that I very much relate to, which is when you get down into the details, this is the interesting thing. You can't approach it like it's a deterministic calculation. And so our solution was to take the risk-informed approach. And in doing that, you also open up the door again, as we have in our rule, to have that communication, coordination, cooperation with the local preparedness community in those locations you're going to be citing. So it is a whole-of-nation approach. We set the standard, but our licensees are working not only with us to meet that standard, but with those communities to explain the risks and hazards, to assure that the preparedness, they're ready on site and they're meeting our requirements, and that the off-site communities are prepared as well.
Thank you. We have time for one more question. Who's first?
Thank you, Marina, for this session. I think you addressed many questions regarding the floating and mobile reactors. Regarding to the last three questions, Tom just mentioned that the emergency preparedness and the communication strategy regarding the design. My question to Natasha from Rosatom, based on your experience and operational experience from the floating reactor, how do you manage the communication responsibility and protocols and the real-time hazard when the floating is moving from port to port internationally, and there is a different operating organization is working at the same time?
Mm-hmm. Thank you for this question. In fact, there are 2 points. First, of course, everything that is not clear can be clarified in intergovernmental agreement. It's the best way to do it. But in our preferable business model, there are no two operational organizations. There is only one. So the floating nuclear power unit is not expected to be sold. It would be operated by Russian Federation during the whole life cycle. It means that it would be the specific operation organization defined at the beginning, as it is stated in safety fundamentals of the IAEA, one organization responsible for the whole life cycle. And when the object moves, when the floating power unit comes to a port, this operation organization is still responsible for it and would operate it under the special approval of the administration of the host country. And of course, host country is still responsible for emergency and preparedness. And this is the point we should think about the interfaces and communication interfaces also. They could some technical problems appear, like sometimes we face the situations like the frequency of the grid is not okay for us, it differs, and also some small things that should be defined at the very beginning of the project, analyzed and clearly stated in some document signed by two parts. If it's not intergovernmental agreement, it can be the agreement between the operating organization and the host port. There is the administration of port, and it also can be written down to be clearly defined at the first stages.
Thank you. So unfortunately, we are running out of time, but you know our experts. Feel free to approach them during the break and ask your questions. And I would like to note that it was a very interesting session, and if we had more time, we probably will continue talking more and more, but I would like to close it, and I would like to express my appreciation for the host, for the very smooth organization of this conference, for Agnieszka, our technical secretary, who supported us so much, and of course, our distinguished experts. Thank you so much.
تلامس الطاقة الحياة، تضيء المنازل، تغذي الأحلام، وتشرق معها آفاق مستقبل واعد. دويهين للطاقة النووية، مساهم فعال في تعزيز تنوع الطاقة في المملكة العربية السعودية، حيث نعمل بروح التعاون، نتمسك بالشفافية، ونتحمل المسؤولية في كل خطوة نخطوها، ومن خلال جهودنا المشتركة نصنع أثراً مستداماً، ونسير معاً بخطى واثقة نحو النجاح. طاقة جديدة تولد لمملكة تنمو وتزدهر اليوم، ولأجيال واعدة تصنع المستقبل. تلامس الطاقة الحياة، تضيء المنازل، تغذي الأحلام، وتشرق معها آفاق مستقبل واعد. دويهين للطاقة النووية، مساهم فعال في تعزيز تنوع الطاقة في المملكة العربية السعودية، حيث نعمل بروح التعاون، نتمسك بالشفافية، ونتحمل المسؤولية في كل خطوة نخطوها، ومن خلال جهودنا المشتركة نصنع أثراً مستداماً، ونسير معاً بخطى واثقة نحو النجاح. طاقة جديدة تولد لمملكة تنمو وتزدهر اليوم، ولأجيال واعدة تصنع المستقبل. Ladies and gentlemen, distinguished guests, session will start in 5 minutes. Ladies and gentlemen, distinguished guests, session will start in 5 minutes.
distinguished guests, colleagues, ladies and gentlemen, please help me in welcoming Dr. Khaled Al-Aissa, Chief Executive Officer for the Nuclear Radiological Regulatory Commission here in Saudi Arabia. Conference President, Your Excellency, please.
السلام عليكم ورحمة الله وبركاته. أصحاب المعالي والسادة.
Ladies and gentlemen, distinguished delegates, as we gather here at the close of the EPR 2025, we return to a fundamental truth that has guided every session and every conversation in this hall. Preparedness is not merely a plan written on a paper. It is a living responsibility, a responsibility shaped by science, strengthened by cooperation, and sustained by collective will protect the people and society in moments when clarity matters most. Over the past 4 days, we have witnessed an extraordinary gathering of minds and expertise, and have had the privilege of hosting over 900 participants in person and welcoming more than 40,000 viewers online. Together, we have shared knowledge, experience, and innovation across 115 presentations, 88 poster sessions, 4 keynote addresses, 4 roundtables, and 5 side events, all reflecting the depth, diversity, and maturity of this event. As was discussed at the conference, in all types of emergencies in the world, we do not find international organization, cooperation, standards, and specialized organization to do so, as is the case in nuclear emergencies. Ladies and gentlemen, the deliberations of the EPR 2025 have been rich, multi-dimensional, and profoundly impactful. From the opening perspective of the specialized technical sessions, this conference demonstrated the extraordinary breadth and depth of expertise that came together here in the city of Riyadh. The discussions extended across a broad range of nuclear and radiological emergency preparedness topics, beginning with international assistance arrangements and the medical and public health management of radiologically exposed individuals, moving through sessions on public communication, strategies to counter misinformation, and the development of coordinated messaging, and reaching into the detailed examination of digital transformation within emergency operation centers and command and control structures. This diversity was not a matter of breadth for its own sake. Rather, it reflected the depth and rigor of the expertise brought together at this international forum. The keynote offered important technical guidance that deepened our understanding of the current and emerging challenges. They underscored the need to close gaps in international conventions and strengthen guidance for emergency preparedness and response in the context of military conflict. Speakers emphasized that radiological emergencies are inherently multi-hazard events requiring integrated planning and flexible evidence-based decision-making. They also highlighted the importance of maintaining robust, regularly tested preparedness arrangements that involve stakeholders and the public to build trust, while addressing the opportunities and challenges posed by small modular reactors and new nuclear technologies, including updated approaches to emergency planning zones and multi-unit sites. Across the thematic session, several operations priorities were identified and central strengthening readiness. These included improving cross-border coordination and interoperability through the IAEA platforms, GIS systems, and real-time data sharing, enhancing medical surge capacity, standardized triage, biodosimetry, and rapid deployment capabilities, and advancing adaptive protection strategies using real-time monitoring, modeling, and AI-enabled decision tools. Participants also stressed the importance of integrating safety and security functions through joint training and unified command structures, developing scalable national EPR managed arrangements, and promoting emerging technologies responsibly with attention to cyber security and interoperability. Additional priorities included supporting first Additional priorities included supporting first responders with interoperable equipment and standardized training, adopting multilingual communication system, an accurate and timely inflow flow, and establishing the global capacity building architecture that increased e-learning completely of frameworks, mentoring, and national support packages. We also emphasize the human core of preparedness through sessions dedicated to youth engagement, women in nuclear and emergency response, leadership, competency, capacity building, and strengthening the national and regional networks. We affirm that the sustainability of emergency preparedness rests on cultivating diverse and resilient human capital.
متنوع متمكن وقادر على الصمود.
As we look toward the next phase, the path ahead becomes clear. There is a pressing need to strengthen the international structure that enable early notification, coordinated assessment, and rapid assistance. It is equally essential to advance preparedness frameworks that align with the realities of emerging nuclear technologies, including small modular reactors and non-traditional deployment environments, and to continue integrating digital technologies across the layers of emergency management, from monitoring to modeling to communication. Investing in human capital through training, cross-border knowledge of exchange, mentorship programs, and long-term capacity building remains fundamental to establishing sustainable readiness, alongside fostering a global culture of preparedness that is more transparent, inclusive, and adaptive. Developing international instruments related to nuclear and radiological emergencies has become an urgent priority. This includes calling for periodic international review meetings similar to those adopted under other global conventions and strengthening efforts to understand and manage public anxiety during crises.
التي قد ترافق الأزمات النووية أو حتى تسبقها.
Misconceptions, misinformation, and long-standing stereotypes about nuclear technology and radiation risk can significantly influence public behavior and response, making effective public communication essential to combatant preparedness. In the realm of international cooperation, it has become necessary to further reinforce the important work undertaken by the IAEA in the field of emergency preparedness. The agency efforts to form vital global, yet time has come to broaden these efforts through additional initiatives to enhance global readiness. From this perspective, the importance of establishing a voluntary international network of nuclear emergency centers becomes evident, one dedicated to exchanging expertise and strengthening response capabilities on both national and international levels. The Kingdom has affirmed in this regard its readiness to make its national nuclear emergency infrastructure available in support of the agency and in strengthening the capacity of member states. Ladies and gentlemen, EPR2025 was not only an advanced technical platform. Over these 3 days, we have seen what is possible when expertise is shared, challenges are confronted collectively, and solutions are imagined with courage and clarity.
وتصاغ الحلول استنادا إلى أسس علمية واضحة.
And before we bring this conference to its close, allow me to pause and acknowledge the extraordinary human efforts behind these 4 days. The richness of our deliberations was only possible because of the dedicated work of many individuals and institutions. Our deepest appreciation goes to the Program Committee, who shaped the agenda of exceptional depth and global relevance. We extend equal gratitude to the roundtable chairs and panelists whose insight and leadership turned complex challenges into clear pathways for progress. We thank the IAEA Secretariat, the Incident and Emergency Center, and the global scientific support teams from technical officers, communication specialists, whose professionalism and coordination ensure that every session, every panel, and every exchange reflected the highest standard of the agency mission. And our partners, sponsors, and contributors who are sincerely grateful for we are sincerely grateful for your commitment and presence. Above all, we recognize the tireless efforts of the NRRC operational teams, the logistics teams, the coordination cells, the media and communication teams, the volunteers, and every staff member who worked behind the scenes and late into the night to deliver a conference that reached more than 79,000 people around the world through live broadcast, social media coverage, and international new platforms.
وفي تمكين المؤتمر من الوصول إلى جمهوره الدولي بكفاءة عالية وترسيخ حضوره كمنصة عالمية تناقش فيها قضايا التأهب للطوارئ النووية على أعلى المستويات.
And may the spirit of cooperation that guided EPR 2025 carry us forward towards a stronger preparedness, deeper trust, and safer, more resilient world for all. Thank you for you all, and we wish you a safe journey home.
Thank you, sir. I would also now like you to help me welcome to the stage Senior Advisor to the Nuclear Regulatory Authority of Argentina, former Director of the International Atomic Energy Agency, and Vice President of this conference, Dr. Abel Gonzalez.
Well, all the good things, unfortunately, have an end, and we are ending a good thing. And this conference has been a good thing, inter alia because it confirmed that we were able to create an international system of cooperation for emergencies, for preparedness, which is really unique. There is not any other human endeavor which has something similar. And there are many other emergencies. In many industries, there has been big emergency with hydropower, for instance, and people have to deal with that on ad hoc basis. We are the only one who were able to build this system. And I believe we have to be proud of that. And this conference is a kind of pinnacle of all these efforts. Efforts through many years in which we learn with experience, with lessons, with things that we didn't knew that will happen and has happened. Who below Chernobyl would believe the drama of pediatric thyroid cancer? But we learn. 7,000 children were suffering. We didn't know that such a drama could happen, and now we know, and we adjust to that. And as I said the other day, who would know before Goiânia that the source of this size will have an havoc in a city of 3 million inhabitants? Nobody believed that this could happen, and happen, and we learn. Who could believe that the tsunami would produce the disaster of Fukushima? There were no prevention for tsunami before. We were learning. And this collection of learning created an international system. And I underline the word international, because we usually made a small mistake. We refer to the IAEA standards. And it's true, the IAEA produced the standard, published, etc. But very few people notice that the IAEA standards are international standards, because the other organizations of the UN system co-sponsor the standard. A co-sponsor is a key word. Co-sponsor is not the same as cooperation. Co-sponsor means that our governments approve the standard not only in the IAEA, but also in the other organizations. Our governments approve the standard in the World Health Organization, in the Food and Agriculture Organization. These are international standards. And for that reason, we have an international regime. Again, it's unique. And this conference has somehow been the top of this unique situation, and we have to be really proud of ourselves, of what we have achieved. And I personally believe that the Secretariat should inform the Board of Governors of the outcome of this conference. Should be an insert document to the Board and to the General Conference on the success of this conference. But following our tradition, success doesn't mean that we sit now. Success means that because we learned in the past, we will do the same for the future. And we have learned many, many things in this conference. And I believe that we should project all the things that we have learned also to the future. In the past, when something like this has happened, this projection took the form of an action plan. And again, I will suggest the Secretariat to try to formulate an action plan on the basis of the many lessons learned during this conference, and to submit that action plan to the Board of Governors and to the General Conference in order to have the real support for executing the benefits that this conference is giving, for taking all these lessons and put that lessons in practice. And there were many. I cannot go through all of them. But just in the last session, we saw what is coming on the so-called SMR, a collection of things under one acronym, SMRs. The M, that sometimes is read as medium, sometimes as modular, and medium and modular are different. We know that in the, 90 projects which are going around there are some of light water and some which are not light water, and these are different. We know that some are for land-based, and as we saw in the last session, some are for shipping, and these are completely different. All these challenges will be very different. And some may believe that we can wait in emergency planning, that these ideas of SMR mature a little more. Because for the time being, are not so mature. I mean, we have a lot of brochures. But from a brochure to a blueprint, there is a very long way. But let me share with you a bad news. And the bad news is that we should not wait too much, because the people of SMR may be waiting something from us. Let me remind you that after the Fukushima accident, the Swiss government requested that the safety convention have to be changed to cope with the Fukushima accident. People don't want to change conventions for many political reasons. But the Swiss managed to call a diplomatic conference to change the convention. How to deal with the Swiss government request and the fact that better not to change the convention? Well, we chair that conference, for I know that very well what has happened. And that diplomatic conference came with a declaration that is not politically binding, but is not legally binding, but is politically binding. The Vienna Declaration on Nuclear Safety. And that Vienna Declaration for these new reactors required an action from us. Because one of the key principles said that the new reactors had to be designed to prevent radioactive releases large enough to require long-term protective measures and action. This is a very nice sentence, but this sentence now needs numbers. What means radioactive release large enough to require long-term protective measures and actions? We have to provide that answer. Therefore, all this wave of SMRs are waiting from us some clear indications. If not, it will be difficult to go ahead. I cannot imagine regulatory authorities authorizing an SMR that do not comply with the Vienna Declaration on Nuclear Safety. This is just a small point taken from one session of this conference. Imagine if we go through all the sessions, how many points we can collect for an action plan. Many of them. And that will be a real gift from this conference to the future. That all the work on these 4 days, all the work be collected in an action plan in order that action be triggered from the effort of all of you during these 4 days. And of course, we should end with thanks, with many thanks. First of all, to the Kingdom of Saudi Arabia, to his regulatory authority, to his president, for organizing this mammoth conference. I tell you the following, in my long career, I attended many conferences. I was saying to the chairman just recently, I never saw a hosting like this. It was really magnificent. It was really extraordinary. And we should be very, very thankful for that. And of course, to my friends, to my friends of the IAA. I tell you, there are many, many days and nights of work from the IAA to organize this conference. And they also merit an applause, and I invite them to the floor. Thank you very much. It was a very honor for me to be involved in this conference, and I wish you the best and good trip back home. Thank you very much.
Well, from the highly technical and wonderful remarks, we now go towards the very end of this closing. I'm supposed to introduce myself again. I was told by my technical team. So I am Monica Dobberton. I've had the utmost pleasure of serving as scientific secretary of this conference, the EPR 2025. So, Mr. President, Mr. Vice President, distinguished delegates, ladies and gentlemen, I want to thank you from the bottom of my heart for your active participation in this international conference on nuclear and radiological emergencies. organized by the IAEA, but with the very generous and kind support and hosting by the Nuclear Radiological Regulatory Commission of the Kingdom of Saudi Arabia. This conference has been especially meaningful. The previous conference took place as a hybrid conference during the pandemic with its restrictions. And today we've had the pleasure, for these 4 days actually, to be together in person again. Over 900 delegates in person together to share technical knowledge and experience and to think ahead to what faces us as we keep on working within emergency preparedness and response. And as has been said, many thousands watching the stream from this conference, it is truly reaching many people, and the importance of this conference cannot be overstated. I would like to share with you what we've collectively achieved during these 4 days. The spring of 2025, we received more than 450 abstracts of people who wanted to participate and share their work. That's a remarkably high number. In fact, I think this conference holds the record, and this conference is the one to beat. So, that's a challenge to all the other conferences coming afterwards. And that strong response enabled us to convene all of you, to listen out during 21 technical sessions, 4 roundtables, 4 wonderful keynote speeches, 5 side events, poster sessions, sponsored exhibitions, and a lot of interesting conversations. I would like to thank everyone for what you have brought here. This conference has demonstrated the diversity, maturity of the field, and how important global emergency preparedness and response is within the radiological and nuclear field. On a practical note, I'd like to say to everyone that everything presented here, the oral presentations and the posters, will be available on the website as soon as we possibly can. We will also write a conference report, and that will also be available during 2026. I would like to remark that this is the first time we have arranged an infographic contest, a design contest, dedicated to raising awareness for the nuclear and radiological field. There also we received an enormous number of submissions, 350 plus, where young people all around the world contributed, and 5 winners had the possibility to come to the conference and present their work at the IAEA booth today, thus showcasing their creativity and commitment and public engagement. Mr. President, Mr. Vice President, distinguished delegates, ladies and gentlemen, I would like to thank, from the bottom of my heart again, Dr. Khalid Alessa, supported by our Vice President, Dr. Abel Gonzalez, for their enormous leadership, their guidance, and unwavering support in this important conference. They've outlined already the priorities that emerge from this event from this week, and I can never thank them enough for their deep engagement and their interest and energy that they show to this field. It is unique. And this has been before, during, and I'm sure it will be after the conference. So again, thank you so much. As much as I could spend hours probably singing your praises, and I could, because I know, Dr. Abel, you said how much goes into this conference, but you have given that yourself. I also have to express and thank many others. To the program committee, many of you are here, led by Dr. Nasser from the NRC. They early took stewardship of the scientific program, and that began more than a year ago to plan and think of the technical side. This committee reviewed 491 abstracts to see which ones should be chosen for this conference. They selected 126 oral presentations and 150 poster presentations, thus forming the foundation of this week, giving rise to rich technical discussions and thoughts. Dr. Nasser, I also want to thank you for your commitment and your work in close association with the IEC in every step going towards to this conference. I would also like 4 very distinguished keynote speakers. Again, Vice President Gonzalez, Ms. Angela Leek, Jean-Luc Lechon, and Mr. Jing Chuning. They've all managed to look forward, reflect on the challenges and opportunities within EPR, and to think about resilience and the importance of the work that we're doing in the field. I would like to thank all of the moderators and the panelists of the roundtables, and the chairs of each and every technical session. Again, the contributions are massive. The work done before the conference and during the conference can never be underestimated. It's given rise to a substantive and thoughtful dialogue all week. I would also like to highlight the importance of the side events. We've had 5 of them. As our Director General noted in the opening remarks, the increasing diversity of the EPR field is a core priority. And again, I would like to thank the Director General of the IAEA for those remarks and for his attention to the field of emergency preparedness and response. 2 side events, her leadership and connecting generations in EPR, were dedicated specifically to broadening participation and empowering perhaps underrepresented groups that we would like to bring even more into the field of emergency preparedness and response. One young participant said, "I'm here because I fell in love with the field." And I thought that was very inspiring and very recognizable. We also benefited from the insights on the design, implementation, and follow-up of the COMEX 3 exercise. And I would also like to thank our partners in the US for their insights and thoughts on the decision-making dynamics in a nuclear security emergency scenario. To the Nuclear and Radiological Regulatory Commission here in Saudi Arabia. Again, Dr. Nasser, Dr. Youssef, Dr. Khaled, and your teams. You've been tireless partners. You've been wonderful to cooperate with. It's been more than a year of preparation, but my goodness, the results. The results have been astounding. Your professionalism, your attention to detail, your warm hospitality, and your very high standard that you've set have made it almost, well, certainly something to surpass. So, I'm getting towards the end, bittersweet as it is. I would like to thank Karine Herviot, our Nuclear Safety and Security DDG, for her attendance, for her engagement, for her encouragement, and for all of the deep responses and questions she's posed and given during this whole process. Her attention, again, to this conference has been invaluable. I'd also like to thank the directors at the IAEA, especially the ones in the Division of Nuclear Safety and Security. They've been so supportive of this conference all the way, and it's much appreciated. That said, there are many people here that I will thank, and there are many people still at the Incident and Emergency Center who would have loved to attend this conference, but we cannot bring everyone here because we actually have to have a 24/7 response capability at home. We are thinking of you. We appreciate your hard work as well. And we're looking forward to seeing you again and working further to, again, build on this wonderful foundation that we've had during this week. Here, I'd like to thank the conference service team, led by Tom Danaher, but also with Eric Panaguaya and Julie Zellinger. Tom has led the efforts and supported this conference all of 2025 and more. And every time I did what Tom told me to do, it turned out incredibly well. So it was a great support. I want to thank my close colleagues. I would like to thank Nadeem Hussain and Stacy Horwitz. They worked ceaselessly on the Convex 3 session, and they've also helped and been technical officers for many other technical sessions as well. And they will keep working on the Convex to evaluate and sum that exercise up in a good way. I'd like to thank Reka Kaltenbach, my incredible assistant, Erica Paloma, who worked on our booth with the VR learning, and she also works on our e-learning. I need to thank Agnieszka Hamburg. She came into the agency September 1st, threw herself right into this work, and she's been in contact with very many of you as well to put together the panels, keynotes, etc. Herman Zarate and Manar Razbun, who are excellent and steadfast technical officers in and out of the conference and who could do anything I throw their way. And it's miraculous. I'd like to thank Nayana Jarajan, where I'm not sure where you are, but you are here. My very accomplished outreach officer. She's also followed this conference from the very start until the very end. She's incredibly efficient, raising awareness and showing the technical importance of this conference before, under, and after. Last, but certainly not least, I would like to thank your very own homegrown son of Saudi Arabia, Musa Al-Khatam. Musa's put in grueling hours, put together a lot of work with us in the agency and with the NRC to ensure that you had this week here. So thank you so much. It does take a village to do such a conference. We don't do it alone. We have a lot of support. We have the help of the hosts, the help of the president and the vice president, And I just have to say again and express my appreciation for that work. I am deeply awed and honored to have been a part of this and to make sure that your emergency preparedness and response interests have been met and will be furthered after this conference. Before I formally declare the International Conference on Nuclear and Radiological Emergency as adjourned, I'm pleased to announce that the next conference will take place in 2029, 4 years from now. I warmly invite all of you to join us again. We cannot predict the precise issues we have and are talking about in 4 years' time. We don't know exactly what will dominate the agenda, but we can be certain that the community we built during this conference and in our regular work will continue to strengthen, will help us remain resilient and forward-looking and efficient and effective. So I encourage everyone to keep working together outside of this conference to further your own and others' community within EPR. With that, I'd like to wish everyone safe travels. Thank you so much for attending this conference and every success in your ongoing work. Thank you so much. And this conference is closed.